Sand turns to glass in roaring furnaces where raw silica meets fire hotter than a volcano. Inside massive automated plants, molten rivers flow, flatten, and cool into flawless transparent panels for skyscrapers and smartphones alike. Today we uncover the high-tech choreography that transforms ordinary sand grains into millions of precision glass sheets shaping the modern world. It begins with a dry whisper, silica sand, pale as bone, pouring from a towering hopper into a vast stainless steel bin. The grains are so fine they almost float, catching light like powdered glass. In this factory, tucked into a sprawling industrial zone far from the nearest beach, hundreds of tons of this raw material arrive each day by railcar and truck. Not a single handful is wasted. Each grain has been mined, washed, sorted, and graded for purity because the requirements for architectural or solar-grade glass are exacting. No iron, no organic fragments, no discoloration. Just crystalline quartz, crushed and sieved to a fine consistency. The sand flows through massive steel ducts into storage silos that stretch 4 stories high, their insides lined with anti-corrosive coatings to keep the materials perfectly dry and uncontaminated. From here, automated augers move precise portions of silica into the batch house, where the transformation truly begins. Alongside the silica, 2 more ingredients arrive in parallel streams: soda ash and limestone. Soda ash, or sodium carbonate, acts like a kind of softener. Pure silica melts at over 1700 degrees Celsius, but with soda ash in the mix, that threshold drops to a more manageable 1450. Limestone adds calcium to the mixture, making the finished glass more stable and resistant to weathering. The exact ratio of these ingredients is crucial, and it's adjusted constantly by computer-controlled systems. Too much soda ash, and the glass becomes too soluble. Too much limestone, and it turns brittle. Dozens of other ingredients might be added in tiny quantities: alumina for durability, dolomite for stability, or small amounts of colorants or decolorizers, depending on the intended use of the glass. Each additive is measured down to the gram using load cells and vibratory feeders, ensuring that every single batch of raw material is chemically identical to the last. The materials are mixed in giant cylindrical blenders that rotate slowly, tumbling the powders together like a cement mixer. There's no room for inconsistency here. If a single batch has uneven mixing, it can cause bubbles, streaks, or structural weaknesses in the final sheet. Sensors embedded in the blending drums monitor the homogeneity in real time, adjusting tumbling speed and cycle duration to compensate for moisture content or clumping. Once the mix is uniform, it's ready for the furnace, the heart of the factory, and one of the most extreme environments engineered by humans. The furnace is nothing short of enormous. Some stretch longer than a football field, with a bath of molten glass glowing orange hot inside a refractory basin made of zircon and alumina bricks. These furnaces run 24 hours a day, 365 days a year, and once they're started, they don't stop for a decade or more. The mixed raw materials are fed in from one end, where temperatures are cooler, around 1200 degrees Celsius. As they move forward across the melt zone, they encounter gradually increasing temperatures, reaching up to 1550 degrees Celsius in the combustion zone, where natural gas and forced air create a roaring flame. Inside, the materials bubble, foam, and finally dissolve into a molten liquid as clear as honey. The heat is so intense that standing anywhere near the furnace walls is unbearable. Engineers monitor the conditions through remote cameras and sensors, looking for signs of foaming, blistering, or inclusions that might indicate a problem in the melt. It takes hours for a batch of material to fully melt and homogenize. The viscosity of molten glass is extraordinary, thick, slow-moving, and unforgiving. Inside the furnace, the liquid moves like lava, its flow guided by gravity and carefully designed slopes within the tank. By the time it reaches the outlet end of the furnace, the molten glass is perfectly clear, free of bubbles and chemically uniform. From here, it's directed toward one of the most mesmerizing pieces of machinery in the entire factory, the float bath. The float glass process revolutionized the industry when it was developed in the 1950s, and it remains the standard today for creating large, flawless sheets. At the heart of this process is a shallow bath of molten tin, kept under a carefully controlled atmosphere of nitrogen and hydrogen to prevent oxidation. When the stream of molten glass leaves the furnace, it's poured onto the surface of this tin bath, spreading out like syrup across a griddle. Because molten glass is lighter than molten tin, it floats perfectly flat. Gravity and surface tension work together to form a glass sheet with uniform thickness and an astonishingly smooth surface without the need for grinding or polishing. The temperature gradient in the float bath is meticulously engineered. At the entrance, where the glass is hottest, still over 1000 degrees Celsius, it spreads quickly, forming a thick ribbon. As it moves forward, cooling systems gradually bring the temperature down. The ribbon thins out and solidifies from the bottom up. By the time it reaches the end of the tin bath, it's firm enough to support its own weight and can be picked up by rollers without distortion. The entire process is so smooth, so continuous, that a single float line can produce over 700 tons of glass per day, enough to cover several city blocks in a 24-hour run. Before the glass can be touched or cut, it must be cooled even further, and in a very specific way. That's where the annealing layer comes in, a long, tunnel-like oven where the glass ribbon moves on rollers through zones of precisely controlled cooling. If the glass were cooled too quickly, it would develop internal stresses, like a frozen lake cracking in the spring. Instead, it's cooled slowly over the course of more than an hour, from over 600 degrees Celsius down to room temperature. Inside the layer, the air is kept at exact gradients, cooling the glass a few degrees at a time to prevent warping, distortion, or invisible structural flaws. When the ribbon finally emerges from the layer, it's ready to be cut. High-speed mechanical arms equipped with diamond wheels zip back and forth across the moving glass, scoring it in precise dimensions, often in standard sizes like 3 meters by 6 meters, depending on the client. The scoring itself doesn't break the glass, it just creates a weak line. The actual breaking is done with a gentle flexing motion, like snapping a cracker along a crease. The cuts are so clean they don't even produce shards. The edges are trimmed, and the glass is automatically sorted, lifted, and stacked by robotic arms onto giant metal racks, ready for inspection and packaging. But before a single sheet leaves the factory, it undergoes an intense round of quality control. Laser scanners check for optical distortions. Light boxes reveal bubbles, stones, or scratches. High-speed cameras catch even microscopic defects that the human eye would miss. If a flaw is found, the sheet is rejected, crushed, and recycled right back into the furnace as cullet, the industry term for waste glass. Nothing is wasted here. Even the heat from the furnace is captured and reused to preheat incoming air, saving energy and reducing emissions. The entire process is a closed-loop marvel of industrial engineering, humming along day and night, transforming mountains of sand into architectural skin. The moment those flawless sheets are cut, cooled, and inspected, they begin their transition from raw industrial product to something far more refined. But for many glass panels, this initial manufacturing phase is only the beginning. Depending on their final use, whether for skyscrapers, solar panels, appliances, or vehicles, the glass may go through a series of secondary processes, each adding layers of functionality, strength, or visual appeal. One of the most common next steps is tempering. This is the process that turns ordinary float glass into safety glass, the kind that doesn't break into dangerous shards, but rather shatters into thousands of small, blunt-edged fragments. The transformation is purely physical. The cut glass sheets are loaded onto conveyors and passed through another furnace, this one heating them rapidly to around 620 degrees Celsius, just above their softening point. The key, however, is what happens next. The sheets are blasted with jets of cold air on both sides, cooling the outer surfaces far more quickly than the inner core. As the interior slowly contracts, it pulls inward, creating a state of internal tension. This locked-in stress is what gives tempered glass its strength, 4 to 5 times stronger than untreated glass of the same thickness, and its distinctive breaking pattern. The entire process takes less than 2 minutes, but the control involved is precise down to fractions of a second and degrees of temperature. Tempered glass is essential for everything from shower doors to building facades to phone screens. But not all applications need that kind of stress hardening. Some call for lamination instead. Laminated glass is created by sandwiching 2 or more sheets of float glass around a clear plastic interlayer, typically made of PVB, polyvinyl butyryl. These layers are assembled in clean rooms to prevent contamination, then fed into a vacuum chamber that removes all air pockets. From there, the sandwich is passed through rollers that bond the materials, and finally into an autoclave, essentially a pressurized oven that cures the lamination at around 140 degrees Celsius under high pressure. The result is glass that, even if broken, remains in place, held together by the inner film. Car windshields use this type of glass, as do bullet-resistant panels and hurricane-rated windows. Still other panels undergo chemical strengthening, a process different from tempering and far more precise. This is especially common in thin glass used for electronics. Here, cut sheets are submerged in a molten salt bath, often potassium nitrate, at around 400 degrees Celsius. The surface sodium ions in the glass are gradually replaced with larger potassium ions from the solution, creating compressive stress along the outer layer. It's a molecular scale transformation, invisible to the eye, but dramatically improving the durability and scratch resistance of the final product. Even a few microns of altered structure can make the difference between a glass screen that cracks on impact and one that survives countless drops. Some panels are treated for entirely different reasons. Coatings, for instance. In architectural glass, coatings can add reflectivity, UV resistance, or insulation properties. These aren't painted on. They're deposited atom by atom in vacuum chambers using a process called magnetron sputtering. Inside a giant chamber, the glass sheet passes beneath target materials, metals like silver, titanium, or chromium, that are bombarded with ions, causing their atoms to sputter off and settle in thin, even layers onto the glass surface. A single coating might be only a few nanometers thick, but its effect is dramatic. Low emissivity, low E coatings, for example, can reflect infrared heat while allowing visible light through, keeping buildings cooler in summer and warmer in winter without blocking natural daylight. Other panels get patterned or frosted using acid etching or sandblasting. Some receive ceramic frits, colored enamels that are screen printed onto the surface and then fired in a furnace to fuse them permanently into the glass. These techniques are used not only for decoration, but also for functionality. For example, dots printed near the edges of car windows serve to control temperature gradients and reduce visual distortion. In high-rise construction, patterns can reduce bird collisions or cut down glare. Every added treatment is another layer of precision, another step that must be flawlessly executed at industrial scale. Once all processing is complete, the glass panels are ready for their final packaging, a logistical feat in itself. These sheets are heavy, fragile, and often enormous, sometimes measuring 3 by 6 meters or more. Robotic cranes lift them, using vacuum suction grips, and gently lower them into custom-built steel stillages, angled A-frames that hold the panels upright in neat stacks. Each rack is padded with foam and separated by cork spaces or polymer cushions to prevent chipping or scratching during transit. Labels are printed with barcodes, batch numbers, and traceability data, so every panel can be tracked from raw sand to installation site. Before shipment, many factories conduct a final round of testing. This might include stress tests, thermal cycling, or even weather simulation. Blasting glass panels with UV light, moisture, and temperature swings to simulate years of outdoor exposure in just days. Panels that pass are loaded into climate-controlled containers or onto air-suspended trucks to protect against vibration and temperature shock. For international shipments, especially oversized architectural glass, containers might be custom fabricated and every piece insured and tracked via satellite. Behind the scenes, the factory itself is a study in clean design and relentless efficiency. Dust is the enemy here, tiny particles that can cause inclusions, haze, or imperfections on the glass surface. To combat it, air inside critical zones is filtered continuously through HEPA systems. Workers wear anti-static clothing. Some parts of the process, like lamination or coating, are conducted in positive pressure clean rooms, where the air is cleaner than a surgical theatre. Even the floor layout is optimized to prevent contamination, with separate zones for raw materials, hot processes, and final finishing. Energy use is another major focus. A single float line can consume as much energy as a small town, so factories employ aggressive heat recovery systems. The exhaust from furnaces is captured to preheat combustion air. Waste heat is routed to neighboring buildings or used in drying ovens. Some plants have integrated solar panels or buy energy from renewable sources to offset their carbon footprint. The goal is to reduce emissions without compromising quality, a challenge, given how thermally demanding the process is. Waste management is just as thorough. Every scrap of cullet, whether from edge trimming, broken sheets, or rejected panels, is collected, sorted by type, and reintroduced into the furnace. Using cullet saves both energy and raw materials, since recycled glass melts at a lower temperature than fresh silica. Even the water used for cooling and cleaning is filtered, treated, and reused in a closed-loop system. Nothing leaves the site without being measured, weighed, and logged. And all of it, the heat, the silence of the annealing leer, the rhythmic hum of robotic arms, the slow drift of molten glass over liquid tin, is calibrated to deliver the same result over and over. Perfect, transparent sheets that started life as common sand. From grains to glass, every stage is a testament to scale, patience, and precision. And the process, as complicated as it is, never really stops. When one furnace is eventually shut down after a decade of operation, it cools slowly over weeks, while a new one is built beside it, brick by fire-resistant brick, so the line can keep flowing, day and night, year after year. Down on the line, time moves differently. It's not counted in minutes, but in meters. Meters of glass ribbon steadily rolling off the end of the float bath, unwavering in its pace. The process is continuous, relentless. There are no breaks, no pauses. Once the furnace is lit and the float line begins, it runs non-stop for years, maintained with surgical precision and monitored around the clock by teams of engineers, technicians, and operators who know the glass almost like a living thing. They can read the smallest ripple in the surface, the faintest haze or color shift, and trace it back to the melt, the batch composition, the tension of the rollers, or even a minute drift in furnace temperature. Because here, every variable matters. Inside the control room, surrounded by screens that pulse with temperature maps, flow rates, and pressure data, the float line is watched like a heart monitor. Operators adjust burner ratios, tweak gas mixtures, and modify conveyor speeds by fractions of a percent. There's an entire choreography behind this stillness, an invisible ballet of heat and chemistry. If the temperature of the tin bath drops by just a few degrees, the glass might thicken or pick up tiny distortions. If the furnace pressure dips too low, oxygen might creep in and oxidize the tin, ruining the surface finish. If a bit too much soda ash is fed into the mix, the glass could become cloudy or too soft to cut properly. Then there's the tin itself. Maintaining a perfectly flat and clean tin surface is a quiet battle that goes on beneath the molten glass. The tin is kept in a sealed chamber under reducing gases, constantly monitored for purity. If oxidized, tin can form a grey scum that mars the underside of the glass sheet. Any disturbance, dust, moisture, oxygen, could affect the delicate interface where the molten glass meets the tin, altering the flawless float and creating tiny waves or inclusions. That's why maintenance crews work in isolation chambers, using long tools and mirrors to make adjustments without ever exposing the bath to open air. The entire float system operates under an atmosphere of such precision that even the flow of nitrogen and hydrogen is regulated down to the liter per hour. Beyond the float line, the rhythm changes. In the annealing layer, everything slows to a crawl. Here, the glass is no longer molten, but it's not quite solid either. It's in that in-between state where structure sets and stresses are locked in. The layer is long, sometimes over 100 meters, and the glass moves through it on rollers at a snail's pace. The air inside is segmented into zones, each with a specific temperature. As the sheet moves through, it cools from around 600 degrees Celsius to ambient over the course of an hour or more, depending on the thickness. Thicker glass cools more slowly, thinner glass more quickly, but always with the same goal: uniform internal structure, zero stress. Thermal cameras line the layer, tracking the glass's cooling curve in real time. If a hotspot or cold zone develops, actuators open or close air vents or redirect heat flow to restore balance. At the exit, the glass is finally firm, an enormous, glowing sheet the size of a billboard, sliding out onto cold rollers. Now, the pace picks up. Robotic arms hover above the ribbon, equipped with ultra-sharp diamond wheels. These don't cut the glass in the traditional sense, they score it, creating a fracture line. Moments later, the ribbon is flexed and the glass snaps cleanly, almost silently, along the score. Other machines move in to trim the edges, cutting away the rounded or uneven sides where the float process naturally thickens the glass. These offcuts are whisked away by conveyor to be crushed, sorted, and reintroduced into the melt as cullet. This glass, pristine, flat, and dimensionally perfect, is now what's known as annealed float glass. It could be shipped as is, but more often than not, this is just the blank canvas. From here, it enters a labyrinth of customization. Some sheets are sent for tempering, others laminated, coated, tinted, or curved. It's at this point that the product becomes highly specific. A solar panel manufacturer might require ultra-clear, low-iron glass with an anti-reflective coating. An architect might specify bronze-tinted panels with a mirror finish on one side and a fritted dot pattern on the other. A car company might order glass sheets pre-cut to windshield shape, ready for lamination and embedded with sensors or heating elements. Each of these treatments takes place in its own specialized part of the factory, or in some cases, in entirely different facilities. The coating lines, for instance, are marvels of vacuum engineering. The glass enters a sealed chamber where air is pumped out until the pressure drops below 1/1,000,000th of atmospheric levels. Then, under intense magnetic fields, atoms of metal are knocked from solid targets and deposited onto the glass in a thin film, only a few nanometers thick. These layers are built up in stacks, sometimes 10 or 15 layers deep, each one designed to reflect or transmit a specific wavelength of light. The difference between a good and bad coating can be as subtle as a 1% variation in reflectivity, but the visual effect, clarity, color neutrality, or the sleek shine of mirrored skyscrapers relies entirely on this microscopic precision. Meanwhile, in the tempering section, sheets roll into a furnace at a sprint. The air inside is kept just above the softening point, hot enough to make the surface pliable but not molten. After less than a minute, the glass exits into the quenching zone, where it's blasted from all sides by high-pressure jets of cool air. The sound is deafening, a constant roar of forced air hitting hot surfaces. Inside the glass, the outer layers contract instantly, locking in compressive forces, while the center cools more slowly, remaining under tension. The result is a kind of controlled contradiction, a material both strong and fragile, flexible in load but unpredictable in failure. If it breaks, it shatters into pebble-sized pieces, reducing the risk of injury. But to do this well, the cooling has to be uniform down to the millimeter. Uneven quenching can warp the sheet or create weak zones, especially at the corners and edges. In another wing of the plant, the lamination line hums in near silence. Workers in clean suits feed glass sheets onto conveyors, where they're matched with their PVB interlayers. The film is slightly tacky, so it adheres instantly, and the whole sandwich is aligned and pressed together before entering a vacuum chamber. Here, all the air is sucked out, ensuring optical clarity and adhesion. From there, it enters an autoclave, essentially a giant pressure cooker, where heat and pressure finalize the bond. When finished, the result is subtle. The laminated glass looks like any other pane, but hidden within is a flexible core that holds the shards in place, absorbs impact, and can even block sound or UV light, depending on the interlayer formula. No matter the treatment, the final destination is the same: a waiting bay where the glass is sorted, labeled, and packed for delivery. Robots handle almost all of it. They grip each sheet with suction cups, swing it upright, and slide it into racks lined with foam. Labels are applied with inkjet printers directly onto the surface, each one containing barcodes, batch numbers, timestamps, and specifications. Entire shipments can be traced back through every stage of production: which furnace they came from, what batch of sand was used, what coatings were applied, and when. It's total traceability, a necessity when you're producing hundreds of tons per day and can't afford even a single defective panel slipping through. The loading zone feels like a shipping port. Forklifts move enormous A-frame racks onto flatbed trailers. Cranes lift them into 40-foot containers. Some shipments are local, heading to nearby construction sites. Others are bound for ports, destined for global export. Each shipment is planned down to the centimeter. Glass sheets are heavy. One panel of 12 mm thick architectural glass can weigh more than 100 kilograms, and fragile. Containers are padded, shock-mounted, and often fitted with sensors to monitor for vibration or temperature changes. Some even include humidity sensors to prevent condensation during long ocean journeys. By the time a sheet of glass leaves the factory, it has traveled hundreds of meters, passed through multiple furnaces, endured vacuums, baths of molten metal, blasts of high-pressure air, and scrutiny from lasers and robotic arms. It has changed its shape, its chemistry, its internal structure, and yet to the eye, it looks simple, transparent, ordinary, just a sheet of glass. But it began as sand, fine, white, unremarkable grains. And the journey from that beach-like powder to an engineered sheet of high-performance glass is a study in scale, science, and sheer industrial discipline. Every step builds on the last. Every variable is accounted for. And behind it all is a relentless drive for perfection. Because in this world, a mistake doesn't just show up, it shatters. The factory hums, yet there's no single sound that dominates. It's a blend: the low thunder of conveyor belts, the hiss of quenching jets, the whir of servos adjusting robotic arms. Everything is timed. Everything flows. In one corner, crushed cullet is being fed back into the furnace. In another, finished glass panels are being lifted by suction cranes onto custom-fitted racks. But the real power of the operation lies in its continuous, unbroken nature. Unlike many other manufacturing processes that stop and start with each new batch, a float glass plant is designed for flow. Start it once, and it moves in a rhythm measured in years. That rhythm depends on a supply chain as disciplined as the factory itself. The silica sand doesn't just show up by chance, it's part of a precisely scheduled logistical stream that feeds the hunger of the furnace. A large float plant might consume over 1,000 tons of raw material every single day. That's enough sand to fill 40 dump trucks every morning without fail. Any delay, any contamination in the supply can compromise the entire output. To prevent that, most factories source from only a handful of highly vetted mines with strict quality controls in place. The sand is washed, screened, magnetically filtered to remove iron, and dried before it even reaches the batching plant. This attention to detail continues all the way to the smallest components. The soda ash, mined from ancient deposits or manufactured chemically, must be perfectly granular to blend consistently. The limestone must be free of organics. Even the decolorizers, tiny additions of selenium or cobalt, are delivered in ultra-precise amounts using computer-controlled feeders. For specialty glass, even the smallest change in chemical makeup can affect color, durability, or optical performance. Engineers oversee not only the melting behavior of these materials, but also how they interact at high temperatures, how they foam, and how gases are released as they break down. Inside the furnace, the atmosphere is a world unto itself. Sensors track not only temperature, but also oxygen levels, flame shape, and even the spectral profile of the combustion light. Adjustments are made constantly to maintain the ideal melt conditions. If the batch begins to foam excessively, perhaps due to a moisture imbalance or uneven particle size, it can lead to defects like bubbles or inclusions in the final glass. Operators respond quickly, adjusting the chemistry, tweaking the feed rate, or altering the burner flame profiles. This is where the human element still plays a major role. Despite all the automation, it takes trained eyes and years of experience to truly understand the behavior of the melt. That molten glass, once perfected, exits the furnace like a glowing river. It flows at a carefully calibrated rate, neither too fast nor too slow, onto the tin bath. The tin itself must remain in a constant state of equilibrium. Too cool. And it can cause the glass to freeze before it smooths out. Too hot and it becomes unstable, prone to oxidation or contamination. The reducing atmosphere in the bath, hydrogen mixed with nitrogen, is constantly refreshed and filtered, ensuring that the tin remains pure and the glass floats perfectly. Any deviation in flow, temperature, or surface tension can affect the thickness or flatness of the sheet. While all this is happening, the thickness of the glass ribbon is being controlled not by molds or dies, but by the physics of flow. Edge rollers positioned on either side of the glass ribbon can gently stretch or compress the sheet as it moves along the tin bath. By adjusting their speed and position, the operators can control the final thickness with millimeter accuracy. This is how a factory can produce everything from ultra-thin 2mm panels for picture frames to heavy-duty 19mm glass for bulletproof installations, all on the same line, with no tool changes required. After forming, the annealing process is equally delicate. Glass has a strange memory. Cool it too fast, and it remembers the tension. Heat it unevenly, and it remembers the twist. The layer is designed to erase that memory, to bring the glass into a state of internal harmony. It does this by creating a perfectly uniform temperature gradient. Warm air is recirculated and filtered. Blowers push it over the surface of the ribbon, and infrared sensors track the temperature of both the top and bottom of the sheet. Any thermal shock or imbalance at this stage could create warping, distortion, or invisible stress fractures that might not reveal themselves until months later. On the job site, under load, when failure is not an option. Once cut and sorted, the glass begins its journey through post-processing. For building applications, the next step is often heat treatment. This includes full tempering, heat strengthening, a less intense version of tempering, or even bending. To bend glass, it's first heated in a furnace until it becomes pliable, then slowly sagged over a mold or forced into shape with precision tooling. The molds are usually made of stainless steel or high-temperature ceramics, and the tolerances are tight. A single panel might take 30 minutes to shape and cool, and each mold must be perfectly clean and dimensionally stable, or the final result could be flawed. Then there are the coatings, the invisible, functional layers that can turn clear glass into a solar reflector, a privacy screen, or a self-cleaning surface. Coated glass is created in high-vacuum sputtering machines where metal targets are bombarded by plasma. The atoms released settle in even layers on the glass surface. These coatings can reflect specific wavelengths of light, block infrared heat, or scatter UV radiation. Some coatings are only a few atoms thick, but their effects are profound. A low emissivity, low E, coating, for example, can improve the energy efficiency of a window by more than 50%, all without affecting its transparency. Each of these processes must be perfectly synchronized. Timing is everything. From cutting to coating to tempering, the movement of glass sheets through the factory is orchestrated like a dance. Pauses allowed, but never stops. If a sheet is delayed too long between heating and tempering, it might pick up moisture or dust. If it's coated while still warm from annealing, the heat can affect the deposition profile. These considerations shape not only the factory layout, but also the production schedule, which is adjusted in real time by software systems that manage thousands of moving parts, temperature zones, robot paths, material usage, storage levels, maintenance cycles, and delivery deadlines. Final quality inspection is unforgiving. Even the smallest blemish, a pinpoint bubble, a faint ripple, a hairline scratch, can cause a panel to be rejected. Some flaws are purely aesthetic, others structural. Automated scanning systems use high-resolution cameras and lasers to inspect both sides of the sheet, checking for optical distortion, thickness variation, edge defects, or inclusions. Some systems even use polarized light to detect internal stress patterns invisible to the human eye. When a defect is found, the panel is tagged, removed, and analyzed. Engineers review the data to trace it back through the process. Was it a mix issue, a roller problem, a gas pressure dip in the furnace? Every rejection becomes part of the feedback loop, helping the system self-correct. Once approved, the glass is marked with a permanent, often laser-etched code, an industrial fingerprint that allows it to be traced back to its exact batch, melt time, coating recipe, and handling history. This traceability is essential for large projects like skyscrapers, where hundreds or thousands of panels must be installed in precise order, each matching color, clarity, and strength exactly. Logistics teams manage the flow of racks, crates, and stillages, preparing shipments with military-like discipline. Each panel is wrapped in protective film, cushioned with polymer pads, and loaded onto trucks or into containers with vibration sensors and shock dampeners. Drivers are trained in glass handling. Routes are planned to minimize road vibration. In some cases, entire shipments are temperature controlled to prevent stress buildup during transit. At its final destination, the glass arrives not as a commodity, but as a precision-engineered component. It may be installed into curtain walls that shimmer 60 stories above the street, into solar panels that will spend decades facing the sun, or into the display of a brand new phone. And in each of those cases, its journey began with sand. Dry, silent, formless. The transformation is total, molecular, thermal, structural, and entirely man-made. There's no magic here, only chemistry, physics, and a relentless commitment to perfection at industrial scale. At this stage in its journey, the glass no longer resembles the raw sand it once was. It has been reshaped, restructured, refined. Its molecular composition has been aligned, its surface tension engineered, and its appearance perfected. Yet the most compelling part of the story isn't the glass itself, but the scale and coordination of the systems that make it possible. Inside a single float glass plant, you'll find more than a dozen highly integrated sub-factories operating under one roof, each with its own set of machines, protocols, and staff, all orchestrated toward the singular goal of producing high-performance panels at massive scale, without ever stopping. Take, for instance, the storage and flow of cullet, the recycled glass material that plays a critical role in efficiency. Every trimmable edge, cracked sheet, or defective panel is automatically conveyed to crushing units, where it's reduced to granules of a controlled size. These are then magnetically filtered to remove any stray metal, screened for uniformity, and stored in covered silos. Reintroducing cullet into the batch saves energy. Since it melts at a lower temperature than raw silica, every percentage of cullet used reduces fuel consumption in the furnace. Some modern plants run on up to 30% cullet, which can cut energy use by as much as 25%. But cullet has to be carefully managed. It must be kept clean, separated by glass type and coating, and free of contaminants like paper, labels, or paint. That requires automated tracking, robotic sorting arms, and AI-powered vision systems that scan the fragments in real time. The system knows exactly where each piece of cullet came from and where it's headed next. Then there's the compressed air system, a hidden but essential backbone of the operation. Throughout the plant, pneumatic actuators power everything from diverter gates in material handling systems to the air knives used in cleaning and tempering. The compressors themselves are huge, often housed in their own noise-insulated rooms, with heat recovery systems that capture waste warmth for use in the batch house or even for heating nearby offices. Air purity is critical. Oil-free compressors are used in all areas where the air might come into contact with the glass, particularly in coating or lamination lines. Inline dryers and filters remove moisture, oil, and particles, ensuring that the final product stays pristine. Any trace of contamination, especially in ultra-clear or solar glass, would be instantly visible once installed. Even water has a defined route. Water is used for cooling rollers, rinsing glass sheets, powering high-pressure jets, and cleaning machinery, but it doesn't come and go. Instead, the plant runs an internal, closed-loop water treatment system. Heated water from the tempering and annealing sections flows into underground tanks, where it's cooled, filtered, treated, and recirculated. Sediment is removed in clarifiers, chemical balance is adjusted automatically, and even algae growth is prevented using UV sterilization chambers. Not a drop is wasted. In drier climates, plants are sometimes equipped with condensate recovery systems that trap moisture from steam vents and air handling units, returning it to the loop. The people who work in these facilities don't just operate machines. They interact with one of the most temperamental materials in the industrial world. Glass behaves in strange ways. It's a supercooled liquid in theory, a brittle solid in practice, and deeply sensitive to both temperature and tension. A sharp corner, a surface scratch, or even a sudden breeze in the wrong place can spell disaster for an entire batch. That's why training is continuous. Operators are taught to recognize the early signs of instability, not just in the material, but in the machines and systems that surround it. They learn how a subtle vibration might indicate roller misalignment, how a faint smell near the coating chamber could hint at a vacuum leak, how a change in the furnace exhaust note might signal a shift in burner performance. This human insight is paired with relentless automation, factory control systems monitor thousands of variables simultaneously: furnace pressures, gas flow rates, tin bath chemistry, roller speeds, belt tension, coating thickness, air quality, humidity, and more. In a modern plant, dozens of programmable logic controllers, PLCs, and industrial PCs run in parallel, communicating over fiber optic networks, constantly adjusting settings and raising alarms when something drifts out of spec. Operators work alongside dashboards that visualize live data from every point in the plant. At any moment, they can pull up a heat map of the float bath, compare real-time product thickness to batch specifications, or see exactly how many tons of glass were produced in the last hour. Some factories even run digital twins, virtual replicas of the entire production line. These simulations use real-world sensor data to model the process in 3D, allowing engineers to test adjustments or run failure scenarios without disrupting the actual line. Want to know how a 5% increase in cullet will affect furnace behavior, or whether a new coating recipe will interact poorly with existing cleaning systems? The digital twin can tell you instantly. It's predictive maintenance, process control, and R&D all rolled into one, and it's becoming the norm across the industry. But for all the technology, the process still comes back to the material. Glass, as old as the earth itself, as basic as sand, continues to challenge and inspire. The panels that emerge from these factories aren't just sheets, they're structural skins, solar harvesters, transparent insulators, sound barriers, digital interfaces, and the demands keep rising. Thinner panels, higher clarity, better solar transmission, greater impact resistance, new coatings that filter specific wavelengths, conduct electricity, or even clean themselves in sunlight. The float glass plant must adapt to every new requirement without slowing down, without losing yield, and without compromising quality. To make this possible, new machines are constantly being integrated into the line. Just downstream of the layer, you might find high-speed polishing robots outfitted with diamond abrasives, capable of smoothing the edges of hundreds of sheets per hour. In the tempering section, infrared cameras now map surface stress patterns in real time, displaying them as color-coded maps. On the lamination line, automated alignment tables use machine vision to center layers with sub-millimeter accuracy, ensuring that logos or embedded components line up perfectly. And at the shipping bay, the logistical precision continues. Finished glass panels are often custom-coded for their final destination. A building facade might require panels labeled for installation sequence: south wall, level 14, position 7. That information is embedded in a QR code printed on the label, which installers on-site can scan to see weight, thickness, coating type, and even a digital version of the quality certificate. It's the industrial version of transparency, literal and operational. Every part of the product's history is accessible at a glance. Meanwhile, back in the batching tower, another load of raw sand is being dropped into the hopper. The cycle never stops. As one furnace ages out, another is built. The fire is transferred. New bricks are laid. Sensors are recalibrated. The heat comes back. And once again, grain by grain, sand becomes glass. It takes the relentless choreography of materials, machines, heat, and human focus to make something this delicate, this clear, and this strong, at the scale of millions of square meters every year. And what's striking, perhaps more than anything, is that all of this is done with almost no waste. No dyes run down drains. No scrap is tossed out. No smoke curls from chimneys unchecked. A float glass factory, for all its size and complexity, is one of the cleanest industrial environments on Earth. Its waste is heat, most of which is recovered. Its byproducts are cullet, which is reused. Its emissions are filtered, monitored, and minimized. It is a closed-loop, high-efficiency, high-consistency engine of transformation, one that turns the Earth's most abundant resource into something almost invisible. something we look through every day but rarely see. In the rust-colored haze of a vast scrapyard, beneath a sky streaked with smoke and metallic dust, millions of motorcycles lie in silence. They rest in tight rows and towering stacks, their forms twisted, charred, corroded by time. You can spot the relics of entire generations. Classic 70s cruisers with tank emblems barely legible. Plastic-bodied scooters from the 90s, sun-bleached to chalky white. Modern sport bikes with their fiberglass fairings shattered like shells. These aren't simply discarded machines. They're once beloved companions of daily life. Some carried groceries, others carried dreams. And now, together, they form a mountain of expired utility, awaiting transformation in one of the most remarkable recycling operations on Earth. Every year, more than 10 million motorcycles worldwide are retired from service. And while some are sold for parts or dumped in landfills, a growing number are processed through state-of-the-art recycling plants, where they are broken down to their molecular essence, reduced to base metals that will feed the global hunger for steel, copper, and aluminum. And behind that transformation lies an orchestra of heavy machinery, conveyor systems, chemical extraction stations, and human precision. An industrial ballet choreographed for maximum efficiency and almost no waste. The journey begins long before the motorcycles ever touch the steel floor of the recycling facility. They arrive in convoys, packed tightly onto flatbed trucks, train cars, and shipping containers, hauled in from every corner of the region. Many are collected from urban impound lots, abandoned in alleyways, or handed over voluntarily by owners under vehicle retirement schemes. The intake point at the recycling plant resembles a customs checkpoint. Every vehicle is weighed, catalogued, and digitally scanned. High-resolution cameras document the frame and license history where possible, and the entire load is logged into a database for traceability. This is not a chaotic scrap heap. It's a tightly regulated material flow where each kilogram of metal will be accounted for. Only a tiny fraction of bikes, usually those with rare parts or collectible frames, are flagged for special handling. These are diverted to a disassembly zone where skilled technicians dismantle them manually, salvaging components like vintage engines, speedometers, or headlight assemblies that can be cleaned, rebuilt, and resold. But for the vast majority, those bent, burned, or mechanically beyond repair, the path forward leads directly into the mechanical belly of the recycling line. At the beginning of the main line, the motorcycles are stripped of their most hazardous components. First, robotic arms equipped with imaging sensors identify and remove batteries. Most motorcycles still use lead-acid batteries, which are heavy, chemically reactive, and require isolated processing. The arms clamp down delicately, yet firmly, extracting the battery block and dropping it into a sealed chute that leads to a chemical treatment unit. Simultaneously, fluid extraction systems engage with the motorcycle's tanks and lines using vacuum pressure to remove gasoline, brake fluid, engine oil, and coolant. These liquids are funneled into separate reservoirs where they're either purified for industrial reuse or incinerated in energy recovery systems. What emerges on the other side of this phase is a stripped down carcass, dry, inert, and mostly composed of steel, aluminum, plastic, and copper. The next stage is dramatic. One by one, the motorcycle skeletons are lifted by overhead gantry cranes and placed onto the in-feed conveyor of the pre-shredder, a machine as large as a school bus and 10 times as loud. Inside, twin rotating shafts outfitted with hardened steel teeth begin to devour the bikes. It's not just destruction, it's reduction. Frames are twisted and cracked into chunks. Wheels are compressed into warped discs. Engine blocks snap open under the pressure of opposing crusher arms. The goal here is to fragment the motorcycle into pieces no larger than a loaf of bread, each piece small enough to be moved, sorted, and processed by the downstream machinery. The sound is overwhelming, a mechanical grinding, punctuated by pops of bursting tires, clinks of sheared bolts, and the occasional shriek of a part resisting the inevitable. The shredded output is conveyed upward by a steel escalator, disappearing into the towering heart of the facility, the main shredder. This shredder operates like a beast possessed. It contains a rotor the size of a van, spinning at hundreds of revolutions per minute, armed with hammers made from manganese steel. As the pre-shredded material falls in, it's pulverized into fragments the size of a fist or smaller. Steel tubes are torn open. Aluminum casings crumble. Copper wires unravel into tangled filaments. It's here that the materials are truly liberated from their previous forms. Each second, over 500 kilograms of motorcycle matter pass through the shredder's hungry mouth. The system is so tightly sealed that dust and vapor are sucked into massive air filtration towers, where they're cooled, filtered, and scrubbed before being released. What emerges on the other side of the shredder is no longer a motorcycle in any recognizable sense. It's a mixed stream of recyclable metals and industrial fluff, plastic shards, rubber fragments, bits of fiberglass, and fabric from seats and saddlebags. The real sorting begins here. The mixture hits a wide vibrating conveyor known as a trommel screen, which sifts out finer particles and dust. Larger chunks continue onward, where a magnetic drum separator extracts ferrous metals like steel and iron. The powerful magnet pulls them up and over the drum, causing the magnetic materials to arc through the air and land in a dedicated steel bin. What remains is a chaotic tumble of non-ferrous metals, primarily aluminum and copper, and non-metallic debris. To isolate the aluminum, the line uses an eddy current separator. This ingenious device spins a magnetic rotor at high speed, generating an opposing magnetic field that repels conductive non-ferrous metals. Aluminum parts, especially wheel rims, engine housings, and handlebars, are launched forward into their own container. Lighter plastic and rubber, unaffected by the magnetic forces, simply fall to the ground. But copper, the most valuable and difficult to extract metal, requires a more surgical approach. High-speed vision systems scan the remaining stream using X-ray fluorescence to identify copper by its atomic signature. Then, in a fraction of a second, bursts of compressed air fire from hidden nozzles, knocking the copper pieces off the belt with sniper-like precision. These might include fragments of starter motor windings, stator coils, or wiring harnesses. Everything is sorted on the fly, every millisecond counted. The precision is stunning, especially considering the volume. Some plants process over 150,000 kilograms of mixed scrap per day, with copper recovery rates exceeding 95%. All of this takes place in a sealed environment where airflow, temperature, and particulate levels are continuously monitored. The facility smells faintly of burnt oil and ozone, tinged with the acrid bite of hot metal. But the air itself is filtered, breathable, safe. By the time this process is complete, the motorcycle has been broken down into its essential building blocks: high-grade scrap steel, clean aluminum fractions, pure copper, and a residual waste stream. These materials are loaded into enormous steel bins, labeled by metal type and grade. The steel, by far the largest component, is destined for electric arc furnaces at regional steel mills. There, it will be melted at over 1,600 degrees Celsius and poured into molds for rebar, I-beams, or sheet stock. Some of it may be used in automotive stamping plants, some might be rolled into coils and shipped globally for construction. But all of it will have begun its second life in that facility, as part of a complex chain of machines designed to turn dead motorcycles into raw possibility. Inside the steel mill, the recycled scrap begins its final transformation. The journey from junk to molten metal is an act of industrial alchemy that unfolds in towering chambers of heat and sound. The steel recovered from shredded motorcycles is offloaded by magnetic cranes into massive storage hoppers called charging bins. Each batch is analyzed using spectrographic sensors to determine its exact alloy composition, how much carbon, manganese, chromium, or residual copper it contains. The analysis is critical because not all steel is created equal. Depending on its destination, the recycled metal might need to be reformulated into high-strength structural steel, corrosion-resistant sheet steel, or spring-tempered steel for mechanical components. Based on the analysis, metallurgists determine how much virgin iron, flux agents, or alloying elements to add before the scrap is melted. The steel mill's heart is the electric arc furnace, a cavernous, dome-shaped reactor that uses giant graphite electrodes to generate temperatures of over 1,600 degrees Celsius. When the scrap is loaded into the furnace, the entire building vibrates slightly from the impact. The lid closes and the electrodes are lowered. Then, with a thunderclap and a blinding flash of blue-white light, the electric arc ignites. The energy here is staggering. Each arc can consume enough electricity in a single melt to power hundreds of homes for a day. Yet despite the scale, the process is tightly controlled. Sensors monitor everything: temperature, gas emissions, arc stability, and slag formation. The molten steel bubbles and glows as impurities are drawn to the surface and skimmed away. Within an hour, thousands of kilograms of scrap are liquefied into glowing orange metal, ready for casting. What makes this moment profound is the transformation it represents. Moments earlier, this steel was still wearing the ghost of a motorcycle, still curved in the shape of a fuel tank or threaded through a brake rotor. Now it is fluid, elemental. It will be poured into molds to create billets or slabs, then rolled, forged, or drawn into new shapes. Some of this recycled steel might go into building the structural beams of a new city hospital. Some might be used for manufacturing appliances or railway track. In some poetic cases, the steel is used again for motorcycle frames, forming the skeletons of the very machines it once inhabited. It's a closed loop of material that can repeat infinitely, each time with less energy and less environmental cost than starting from mined iron ore. That's part of what makes this system such a technical marvel. It doesn't just reclaim materials, it reduces carbon footprint at every stage. Producing steel from scrap uses up to 74% less energy than smelting from raw ore. It emits dramatically fewer greenhouse gases, consumes less water, and produces less slag waste. The electric arc furnaces are often powered by renewables, and even where fossil fuels are used, the efficiency gains are undeniable. But perhaps more impressive than the numbers are the mechanisms of environmental protection built directly into the system. Every step of the recycling line is designed to minimize leakage, capture pollutants, and recover usable byproducts. Take, for example, the air handling system. As motorcycles are shredded and melted, a cocktail of metal dust, hydrocarbons, and fine particulates is released. Instead of venting this into the atmosphere, the facility uses negative pressure zones and ductwork to suck the air into a complex filtration network. Massive bag houses, warehouse-sized rooms filled with thousands of fabric filters, capture the dust particles, which are periodically shaken loose and collected for safe disposal or further refinement. Downstream of the bag house, a chemical scrubber uses lime slurry to neutralize acid gases like sulfur dioxide, converting them into harmless calcium salts. This captured material sometimes even finds use in cement manufacturing. Above it all, stacks equipped with real-time sensors continuously measure emissions, feeding data into national environmental dashboards. The entire system runs under the watchful eyes of regulators, software, and increasingly, AI models trained to flag anomalies before they become violations. Even the wastewater is a closed loop. The hydraulic systems that cool and lubricate the shredder lines, as well as the quenching systems in the melt shop, produce vast volumes of hot, contaminated water. But rather than being discharged, this water is collected in subterranean holding tanks, where it undergoes a multi-phase treatment process. First, oil skimmers and sedimentation chambers remove the largest contaminants. Then the water passes through activated carbon beds, reverse osmosis membranes, and UV sterilization units. After being filtered to near potable quality, the water is reused within the plant, a continuous cycle that drastically reduces consumption. The floors themselves are sloped and grooved to capture every drop, and even the vehicle wash stations used to clean the incoming bikes before shredding are tied into the same reclamation circuit. Of course, managing all of this requires coordination on a breathtaking scale. The factory floor is a living system of conveyors, hoppers, feeders, ducts, and robotic arms, all synchronized through a central control room. Dozens of operators sit before vast banks of monitors, watching sensor feeds and performance graphs, ready to intervene if something falls out of range. The entire operation runs on a digital twin, a virtual model of the facility that mirrors every valve, motor, and belt in real time. This allows engineers to predict wear, optimize throughput, and simulate future upgrades without ever touching a wrench. Even the shredding teeth are monitored. Each one is tagged and tracked through its lifespan with predictive models telling technicians exactly when a tooth will dull or crack. On average, the teeth are replaced every 500 tons of material, an operation performed by specialized maintenance bots that enter the shredder cavity with magnetic grippers and high-torque fasteners, minimizing downtime. Outside the facility, logistics take over. The sorted metals are not merely piled into containers and forgotten, they are routed with surgical precision. Steel, aluminum, and copper are tracked by batch number, composition, and destination. Each shipment is barcoded and scanned as it's loaded onto rail cars, barges, or trucks. The steel is often moved in red-hot slabs, straight from the casting mill to nearby rolling facilities. Aluminum, lighter and more sensitive, is typically cast into ingots or logs, then wrapped and shipped to automotive plants or electronics foundries. Copper is processed into cathodes or rods, ready for wiring manufacturers. Nothing is wasted. Even the industrial fluff, the residue of plastic, foam, and rubber that couldn't be cleanly separated, is compressed into fuel pellets used in cement kilns. It's dirty fuel, yes, but in controlled combustion environments with advanced scrubbers. It burns cleaner than coal and recovers energy that would otherwise be lost. One of the most intriguing aspects of the process lies in its circularity. Some of the very companies that manufacture motorcycles also partner with the recycling facility to close the loop. They may purchase recycled steel to fabricate new frames, or recycled aluminum for engine casings. In high-end factories, new wiring looms contain copper that once coursed through the ignition coils of older bikes. It's not just sustainability, it's identity reborn. In some cases, motorcycle brands will even trace the recycled content in their products, marketing bikes with frames made from legacy steel, a material with a past. There's something poetic in that. The idea that machines, which once roared across highways, can live again, not just as ghosts of their former selves, but as the literal foundation of what comes next. This intricate choreography of machines, materials, energy, and time isn't just an industrial operation. It's a testament to the engineering brilliance required to sustain a high-consumption society without drowning in its own waste. The millions of motorcycles that pass through this system each year are more than mechanical carcasses. They are material reservoirs, containers of embedded energy and human effort that, when processed intelligently, offer a bridge between past utility and future potential. Recycling at this scale is not a stopgap, it's a way forward. Once the recycled metals leave the factory, their story doesn't end, it multiplies. They enter a vast, global supply chain where the borders between waste and resource vanish. The steel from a dismantled motorcycle frame in Indonesia might be melted, cast, and rolled in South Korea, then shipped to Vietnam, where it becomes part of a new suspension bridge, or sent to Japan to form the chassis rails of high-speed trains. Aluminum recovered from wheels and engine casings may find its way into laptop frames in Taiwan, window fittings in Dubai, or beer cans in Germany. Copper, the hidden circulatory system of every bike, makes perhaps the most far-reaching journey. Once extracted and purified, it becomes wiring, circuit boards, solar panel connectors, or electric vehicle motors in dozens of countries. In just months, the material that once sped down back roads and alleyways may be part of something entirely new, moving at the speed of light through fiber optic infrastructure or helping drive a high voltage transmission line across a desert. The scale of this flow is staggering. Global scrap steel trade is measured not in tons, but in megatons, hundreds of millions every year. Motorcycle recycling contributes a specific but crucial fraction to that stream. While cars dominate in volume, motorcycles punch above their weight in value because of their dense concentration of high-grade steel, cast aluminum, and concentrated copper. A single motorcycle, fully stripped and processed, can yield between 80 to 150 kilograms of usable ferrous material and another 10 to 20 kilograms of non-ferrous metals. When multiplied by millions of units, the economic value becomes clear. This isn't simply a cleanup effort, it's a multi-billion-dollar industry fueled by the raw reality that mined resources are expensive, environmentally costly, and increasingly scarce. The economics of this system are both intricate and surprisingly resilient. Scrap metal prices fluctuate daily, influenced by commodity exchanges, fuel costs, industrial demand, and geopolitical pressures. But the recycling process itself remains profitable, thanks to its high recovery rates and streamlined logistics. Facilities are often located strategically near ports, steel mills, or industrial hubs to reduce transport costs. In some regions, governments provide subsidies or tax incentives to encourage vehicle recycling, especially for older, high-emission models. In others, the profit motive alone is sufficient. Many large motorcycle manufacturers even form direct partnerships with scrap processors to ensure a steady flow of post-consumer material, allowing them to hedge against volatile raw material costs while marketing their products as partially made from recycled content. Even more fascinating are the second-order effects of this industry, the unintended, sometimes surprising ways recycled motorcycle parts re-enter the economy outside traditional metal channels. In certain regions, especially in Southeast Asia and parts of Africa, large-scale recycling operations coexist with informal salvage economies. Before the motorcycles even reach the shredding line, parts are often removed and sold piecemeal into bustling secondary markets. Frames may be cut and welded into cargo tricycles. Engine components are repurposed into water pumps or generators. Aluminum foot pegs are melted down in backyard forges to create cooking pots. There's a raw ingenuity to this kind of reuse, a level of manual upcycling that modern industrial systems rarely achieve. But not everything salvaged is functional. In some cities, shredded motorcycle chains are reformed into industrial-grade anchoring systems. Old brake rotors become base plates for small turbines or drilling rigs. Even motorcycle seats, stripped of their leather and foam, contribute to the reconstitution of industrial insulation panels, or are chipped and bonded into synthetic flooring. Some fashion designers have even taken to buying seat vinyl, repurposing the worn textures into bags or accessories with upcycled industrial chic aesthetics. In this way, the physical trace of the motorcycle survives long after its function ends, not just melted into anonymity, but reconfigured into surprising new forms. Still, the backbone of the system remains automation and large-scale refinement. Recycling centers are increasingly investing in smart tracking systems to trace every input and output. Barcodes and RFID tags affixed to bins of sorted material allow real-time monitoring of inventory and movement. Machine learning systems analyze throughput data to optimize the shredding and sorting processes. Maintenance schedules for equipment are driven by predictive algorithms that can forecast wear rates based on load histories and environmental conditions. In many cutting-edge facilities, even the noise profile of machines is monitored. Anomalous vibration or acoustic patterns are interpreted as early signs of mechanical failure. The factory becomes not just a processor of waste, but a self-monitoring ecosystem, constantly evolving to squeeze out inefficiencies and adapt to changes in material input or market demand. These factories often operate continuously, 24 hours a day, 7 days a week. Shift changes happen like clockwork, with operators rotating through control rooms, floor inspections, and maintenance tasks. Downtime is costly, and with material arriving by the ton every hour, the pressure to keep systems running is relentless. But the payoff is huge. A single high-capacity motorcycle recycling facility can process upwards of 500 bikes per hour, reclaiming hundreds of tons of raw materials daily. That's enough steel to manufacture the frames of nearly 1,000 new motorcycles. In a week, it could fill the steel skeletons of 100 public buses. In a year, one plant alone might recover enough copper to wire a mid-sized city. All of this exists within a larger question. What happens to end-of-life vehicles in a world increasingly shaped by sustainability mandates and resource limitations? Motorcycles, while efficient and economical, are also part of a disposable culture that generates complex waste. Recycling is the only viable long-term solution for managing the materials locked inside these machines, especially as electric models begin to dominate the market. The future promises new challenges: lithium-ion batteries with entirely different chemistry and risk profiles, electric motors embedded with rare earth metals, and electronic control units filled with delicate circuit boards. These changes will require new machines, new processes, and entirely new recycling paradigms. But the foundation, the philosophy of resource recovery through precision engineering, will remain the same. And perhaps that's what makes the entire process so compelling. It's not just about destruction. It's not just about economics. It's about the capacity to see value where others see junk. It's about systems built not to discard, but to rediscover. Each motorcycle that enters the line may have died a private death, in an alleyway, a garage, a junkyard, but it re-emerges as part of a shared industrial future. A frame becomes a bridge. A wheel becomes a skyscraper beam. A copper wire becomes a solar inverter. Nothing disappears. It just changes shape. For all its steel teeth, flashing sensors, and algorithmic choreography, the soul of a motorcycle recycling facility is still very much human. Walk across the factory floor during a mid-morning shift change and you'll find a rhythm that has more in common with a pit crew than an assembly line. Workers in orange or dark blue coveralls file through decontamination gates, clip on radios, check their digital shift boards, and head to their stations. There's a smell of machine oil and warm metal in the air, mixed with the oddly sweet tang of ozone drifting from high voltage areas. Forklifts move with balletic precision, their drivers glancing briefly toward overhead displays showing load weights, battery charge levels, and priority queues. Some workers spend their days operating heavy cranes or managing input bays. Others rotate through the sorting line, keeping an eye on separation efficiencies and occasional machine jams. At first glance, the factory seems fully automated, but it's the humans who keep it honest, who tweak settings based on feel, who know from experience when a magnet's pull is weakening or when a shredder's tempo has slipped half a beat. Many of these workers have been in the industry for years. They've watched the evolution of the process from the days of mostly manual disassembly, sledgehammers, oxyacetylene torches, and hydraulic shears, to today's system of robotic arms, and intelligent shredders. Yet they'll tell you something quietly. Some of the old machines still work better. In a few tucked away corners of even the most modern facilities, you'll find legacy gear still in use. Not because it hasn't been replaced, but because it hasn't been outperformed. One example is the vibratory screen separator nicknamed the Rattler, a piece of post-war quad sorting equipment built in Germany, still capable of separating ferrous and non-ferrous fractions with uncanny accuracy. The machine roars and shudders like an old locomotive, yet its output is remarkably clean. Nearby, a manually controlled press, thick with layers of repainted steel and worn-down analog gauges, compresses recovered aluminum into dense cubes for transport. There are digital alternatives, but this one's simplicity makes it nearly bulletproof. A veteran operator, hands blackened with graphite dust, adjusts its hydraulic tension with the kind of tactile precision no software can replicate. It's these people, the ones with grease under their fingernails and instinct in their muscles, who serve as the connective tissue between machine and material. They know which motorcycles yield better metal, which batches of scrap to treat cautiously, and when the sensors are lying. One worker, a soft-spoken man who's been on the line for over 2 decades, gestures to a bin of shredded aluminum and says, without looking, "That one's from scooters, Japanese ones. You can tell by the color and the cut pattern. They use a different casting alloy. Melts smoother." He's right. Engineers later confirm the batch is rich in silicon-heavy aluminum alloy, prized for certain high-precision die casting applications. No machine in the building could have made that call unaided. The engineering staff, most of whom operate from a central control and diagnostics hub, bring their own kind of expertise. These are the people who built the system's nervous system, who manage everything from torque loads to arc furnace phase balancing to real-time emissions feedback. Some are trained metallurgists, others are software engineers, and a few are former line workers who work their way into diagnostics through years of internal training. Together, they keep the factory balanced on a knife edge of efficiency and safety. At any given time, they're tracking hundreds of variables: conveyor speeds, wear rates, motor temperatures, energy draw, hydraulic pressure, emissions load, and batch yield ratios. When something goes wrong, and it always does eventually, it's often these engineers who must trace the failure through a web of interconnected systems. A minor vibration in the copper ejection air jets might be traced back to a fouled sensor deep in the eddy current separator. A slightly skewed camera feed might mean a 0.5 millimeter misalignment on a critical robotic picker arm. The process of diagnosis is as much art as it is science. Safety, too, is an omnipresent concern. Despite the automation, this is still a place of extreme forces. Materials are under crushing pressure. Arcs crackle with enough power to vaporize metal. Hydraulic systems can exert thousands of pounds of force. Because of that, safety systems are layered, redundant, overlapping, and constantly evolving. Workers wear RFID tags that trigger alarms if they stray into restricted zones. The plant uses motion tracking systems that can halt machinery mid-cycle if a human form enters a prohibited area. Every tool, from torque wrenches to cutter blades, is scanned out and back in again. Nothing is left loose. Every hour, safety teams make rounds, checking guardrails, recalibrating emergency stops, and inspecting eyewash stations. Every incident, no matter how small, triggers a review. When a forklift operator once clipped the corner of a sorting chute and cracked a feed funnel, the entire route was redesigned within a day. Yet for all the risk, there's also pride, a quiet kind of craftsmanship that permeates the workforce. These are not just operators and maintainers, they're stewards of a highly tuned, ever-changing process. Some facilities run internal competitions. Who can fine-tune the shredder to its highest recovery efficiency? Who can run the copper sorter at peak yield for the longest continuous shift? The numbers are tracked on whiteboards, sometimes even lit up on LED displays hanging in the break rooms. Small rewards, an extra bonus, a team lunch, a new set of tools add a layer of camaraderie to what is otherwise a hard, often monotonous job. But it's more than incentives. It's the sense of doing something that matters. When asked why he stays in the job, one supervisor, a former motorcycle mechanic himself, simply says, "Because everything we take apart ends up helping build something else that means something." There's also a deep sense of responsibility, especially when it comes to the more volatile or dangerous materials still embedded in older bikes. Older motorcycles often contain leaded components, asbestos-based brake linings, or plastic panels laced with fire retardants that release toxins when shredded. These parts require special handling. Teams are trained to recognize specific models and years that trigger caution protocols. In some cases, bikes are diverted to dedicated decontamination lines, where suspect materials are removed by hand under ventilated hoods and placed into secure chemical waste containers. Even trace materials like PCB coatings on early circuit boards are accounted for, scanned, and sent to specialized electronic waste partners for safe disposal or incineration. It's meticulous, slow work, but essential for keeping the larger recycling process clean and compliant. As technology advances, the role of the human will inevitably shift, but it won't disappear. The machines may get smarter, the software more predictive, the processes more hands-off, but there will always be a place for judgment, for touch, for the uncanny human ability to spot the flaw in the system before it becomes a problem. And in many ways, that fusion of man and machine is what defines the modern recycling line. It is not automation for its own sake. It's a co-evolution where each improves the other. There's a beauty in that, a rough, industrial poetry. These are places built to consume the broken, the obsolete, and the unwanted. But through fire, force, and intelligence, they give those objects a second chance. And it's not just the motorcycles that get reborn, it's the people too. The workers who turn wreckage into raw material, who bring order to chaos, who spend their days under the shadow of machines and emerge each shift with the quiet satisfaction that they've helped the world go one step further away from waste. The future is rolling in on quiet wheels. Across the globe, the unmistakable rumble of internal combustion is giving way to something subtler. The whisper of electric motors and the high-pitched whine of regenerative braking systems. Electric motorcycles are becoming more than a novelty. They're a necessity, driven by climate mandates, urban air quality goals, and the global push to decarbonize transport. Entire nations are beginning to shift their two-wheeled fleets towards battery power. It's a massive transition, and it's not just changing what rolls off the factory floor, it's redefining what ends up on the recycling line. Unlike their gas-powered predecessors, electric motorcycles bring with them a new complexity, especially when it comes to materials recovery. At the center of it all is the battery, a dense, chemical-packed heart that stores energy and, once depleted, becomes a potential hazard, or a valuable source of rare earths and high-purity metals, depending on how it's handled. Lithium-ion battery packs from electric motorcycles aren't just heavier, they're structurally integrated into the frame. In many modern models, the battery isn't merely a detachable box under the seat. It's bolted, bonded, and often cooled through embedded channels. Disassembling one safely is an operation that demands more than just gloves and a wrench. Facilities that process end-of-life electric bikes must begin with isolation procedures. Batteries are removed in sealed containment zones, often with robots or insulated tools operated behind blast-resistant glass. Workers wear arc flash suits and insulated gauntlets because even a partially charged cell can deliver enough current to ignite a fire or cause severe injury. Before any cutting happens, each battery is drained through a controlled discharge circuit, a rack of resistors and heat sinks that pull remaining energy from the pack slowly and safely, converting it into harmless thermal output. Only when fully inert can the battery proceed to the next phase. From here, it enters one of the most complex systems in the modern recycling world: battery material recovery. Unlike the mechanical shredding of steel and aluminum, lithium-ion battery recycling relies on chemical extraction and thermal treatment. The cells are first disassembled, casing separated from electrodes, electrolyte residues neutralized. Then the electrodes themselves, often composed of lithium cobalt oxide or nickel manganese cobalt blends, are heated in a low oxygen furnace to drive off organics and solvents. What remains is a concentrated metallic residue known as black mass. This material is chemically leached, bathed in acid or alkaline solutions to separate and purify the valuable components: cobalt, nickel, lithium, manganese. It's a process as delicate as it is powerful. Even a few percentage points of recovery variance can mean the difference between profit and loss. The materials recovered from just one electric motorcycle battery are surprisingly significant. A single pack might yield enough lithium to produce a dozen smartphone batteries, enough cobalt to power a grid-scale energy storage module, or enough nickel to return to the steelmaking process. These are not incidental materials. They are critical minerals, strategic resources with tight supply chains and high geopolitical value. Reclaiming them at the end of a motorcycle's life isn't just good practice, it's fast becoming a matter of national policy. Many governments now include battery recycling quotas as part of their electric vehicle infrastructure plans. In Europe and parts of Asia, manufacturers must show that their battery packs are not only recyclable, but are, in fact, being recycled, with traceable documentation of the recovered yield. It's a compliance layer that forces the integration of recyclers directly into the manufacturing and logistics loop. But batteries are only one part of the electric motorcycle challenge. The motors themselves bring their own complications. Unlike internal combustion engines, which are largely composed of steel, aluminum, and standard alloys, electric motors contain copper windings tightly wrapped around rare earth permanent magnets. These magnets, made from neodymium, dysprosium, and praseodymium, are essential for delivering the torque and efficiency required by modern electric drivetrains. However, extracting them from a motor core is a precise task. The magnets are brittle and dangerously reactive when ground. They can spark, oxidize, or even self-ignite when exposed to air and heat in powdered form. That's why many recyclers now use cryogenic cooling to safely dismantle motor assemblies. The motors are frozen using liquid nitrogen, bringing their temperature down to minus 196 degrees Celsius. At this point, materials become brittle and lose adhesion, allowing the motor to be shattered along structural lines. Once fractured, the components are separated and sorted, with magnets isolated for purification and reuse. There's also the question of circuitry. Modern electric bikes are embedded with control modules, regenerative braking systems, power inverters, and battery management units. These components contain densely packed printed circuit boards filled with tantalum capacitors, gold traces, and tin silver solder. Some even include GPS chips, SIM modules, and telematic systems. When these bikes reach end of life, the electronics must be separated before general shredding. This task is delicate and still largely manual. Skilled workers, often using microscopes and micro grippers, remove boards and modules from control housings, scanning serial numbers to match against compliance records. Once harvested, the boards are passed to specialized e-waste processors, facilities equipped with high-temperature pyrolysis chambers or acid leaching systems capable of recovering minute quantities of precious metals from a tangle of silicon and resin. It's slow work, but the payoff is in the purity. A kilogram of processed circuit board can yield more gold than several tons of mined ore. As more electric motorcycles enter the waste stream, recycling facilities must evolve quickly. Many are now redesigning their lines with modularity in mind. sections that can be switched between combustion engine bike processing and electric vehicle disassembly with minimal downtime. Some plants are installing AI-driven diagnostic tunnels, imaging stations that scan incoming bikes for key visual markers, automatically flagging electric units and routing them to appropriate safety zones. Others are forming direct partnerships with electric bike manufacturers to gain early access to design specs, helping recyclers anticipate future materials and plan for disassembly accordingly. This kind of collaboration marks a shift in the industry, from reactive to predictive, from linear supply chains to circular ecosystems. Yet the challenge isn't just technical, it's also logistical. Electric motorcycles are still a small percentage of the overall recycling stream, but their volume is growing exponentially. And unlike gas-powered bikes, which can often be processed in batches with little variation, electric models are highly diverse. Battery chemistries vary. Motor designs differ. Telematics hardware changes every year. For a recycler, this means constant adaptation. New training protocols, new containment procedures, new fire suppression systems to deal with thermal runaway events, those rare but dangerous moments when a damaged battery begins to overheat, vent, or combust. Some facilities now operate with full-time fire crews and thermal imaging sensors mounted across the processing line, designed to catch hotspots before they flare. There are emergency containment bunkers, steel vaults filled with fire-retardant foam, where suspect batteries are quarantined until they can be safely cooled and neutralized. All of this speaks to a central truth. The motorcycles of tomorrow will not die the same way as the motorcycles of the past. Their deaths will be quieter, but more complex. Their parts will demand greater care, more precision, deeper knowledge, and the facilities that handle them must rise to that challenge, not only to extract value, but to ensure safety, sustainability, and resilience. The shift to electric isn't just an engineering problem, it's a cultural one. It requires an entirely new mindset in the world of end-of-life vehicle processing. But it's a shift already in motion, and for those building the systems of tomorrow, it's also a thrilling opportunity. In many ways, electric motorcycles offer a paradox. They are simpler in motion, fewer moving parts, no combustion, no oil. Yet at the end of their life, they are vastly more intricate. They arrive not as machines, but as puzzles. Chemical, electrical, and mechanical all in one. Recycling them is no longer just about crushing and melting. It's about disassembly, separation, purification, and regeneration. It's about creating systems that see not just a vehicle, but a layered assembly of resources, each with its own pathway back into the world. At first glance, a salvage yard seems like the end of the line. It's a graveyard of twisted frames, shattered windshields, and flaking paint. But within this mechanical wreckage lies something valuable: raw materials, not yet ready to be discarded. Before any car can be fed into the machinery of a recycling plant, it must first be stripped of its most volatile and contaminating components. This is where the dismantling stage begins, a hybrid of industrial procedure and meticulous handwork. Trained workers, often wielding pneumatic tools and hydraulic cutters, begin by removing the obvious parts: tires, batteries, airbags, and fuel tanks. But that's only the beginning. Modern vehicles contain a long list of potentially hazardous materials that must be removed with care, not just for safety, but to protect the integrity of the metal downstream. That includes everything from mercury switches to lead wheel weights to chunks of foam or plastic that might release toxic gases under high heat. This stage might seem low-tech, but it's surprisingly specialized. Extracting a lithium-ion battery pack from a hybrid or electric vehicle, for example, requires specific knowledge and tools. The packs can contain several hundred volts of electricity and have been known to ignite or explode when damaged or improperly handled. In many yards, such components are dealt with in separate, ventilated work areas, often under supervision, by personnel trained in hazardous material handling. Even traditional lead-acid batteries are handled with care, not just because of their corrosive contents, but because they can be recycled separately, often refined into new batteries through a completely different process. Once the major components are out, the vehicle is drained of its fluids. This is one of the more critical environmental steps, as each car can contain up to 5 gallons of potentially polluting liquids: motor oil, coolant, transmission and brake fluids, and gasoline residue. Specialized equipment is used to evacuate these fluids without spills. Tall, spider-like machines with suction nozzles and long arms that can tap into reservoirs and drain them directly into sealed containers. It's a dirty job, but one that ensures no fluids make it to the next stage, where extreme forces and friction would otherwise turn them into fire hazards. By the time the dismantling team is done, the vehicle has been reduced to its structural shell. The interior is gutted, the electronics removed, the fluids gone, and all major detachable parts taken off either for resale, specialized recycling, or safe disposal. What's left is essentially a steel carcass, empty, inert, and ready for destruction. And it's here that the heavy machinery takes over. The next stage is as brutal as it is efficient. The decommissioned vehicle is now destined for the shredder, a machine whose scale and power are difficult to appreciate without seeing it firsthand. Some are enclosed within towering metal structures to contain the sheer violence of the process. At their core is a spinning drum or rotor fitted with giant steel hammers, each one weighing hundreds of pounds. These hammers rotate at incredible speed, striking with enough force to tear a full-sized vehicle to pieces in seconds. The car is dropped in from above, often by a crane fitted with enormous steel claws or an electromagnet, and the moment it hits the blades, it disappears into a storm of noise and flying debris. What comes out the other end is known as auto shredder residue, a chaotic mix of ferrous and non-ferrous metals, glass, rubber, plastic, upholstery, insulation, and fragments of electronics. It resembles a coarse, greyish mulch and is blasted down conveyor belts in a continuous stream, creating a sound like a constant avalanche. But the true magic of the recycling line is only just beginning, because this raw output still needs to be sorted, separated, and purified into usable streams of material. And the most valuable among them is steel. What makes this possible isn't just brute force, but clever engineering. Entire systems of magnets, air jets, vibrating screens, and eddy current separators are used to tease apart the different elements in that debris flow. But before we get to that, it's worth pausing here, at this moment in the process, because it's a remarkable transformation in itself. In less than 10 minutes, a once functional machine, a car that once carried a family down a highway or sat quietly in a driveway for years, has been reduced to particles, not incinerated or buried, but rendered into its basic building blocks. It's violent, yes, but there's something oddly elegant in that too. Once the shredded remnants of a car leave the maw of the hammer mill, the real challenge begins, not in destruction, but in sorting. What's spewed out isn't a clean pile of recyclable material. It's a turbulent mess of steel fragments, aluminum, copper wiring, shards of plastic, bits of glass, cloth fibers, rubber insulation, and the occasional bolt or bracket that somehow survived intact. To the eye, it's just chaos. But to the machines lined up downstream, it's a meticulously layered opportunity, waiting to be sorted, refined, and reclaimed. The first step in the post-shredding phase is the magnetic separator, a workhorse of the industry and the key to pulling steel from the stream. As the shredded material is carried along a wide conveyor belt, an overhead drum magnet spins rapidly above it. Ferrous metals, especially iron and steel, are highly responsive to magnetic fields, so as they pass under the drum, they're pulled upward in mid-air, literally lifted from the pile of mixed debris and redirected onto a separate belt. the effect is dramatic. Heavy steel chunks fly upward and disappear down a different path, as though being summoned by invisible hands. It's the moment when the recycling line begins to extract value from the chaos. These magnets are powerful, some generating fields strong enough to lift car engines or steel beams with ease, but they must also be tuned delicately. The system needs to be fast enough to keep up with the conveyor's speed, yet accurate enough to avoid pulling in non-ferrous materials by accident. Steel makes up about 60-70% of the shredded mass by weight, so this is the primary harvest, and it happens fast, continuously, and with a rhythmic mechanical certainty. What's left behind after the magnet has done its work is still a complicated mix. Aluminum, copper, plastic, rubber, glass, and foam continue along the line, and here the process becomes even more ingenious. Vibrating screens sort particles by size. Air classifiers blow lighter materials, like foam and fabric, away from denser metals. And eddy current separators, which use rapidly rotating magnets, create opposing magnetic fields that can repel non-ferrous metals like aluminum and copper, launching them off the conveyor into separate bins. The steel, now isolated, is still not ready for the furnace. It's jagged, dirty, and inconsistent in shape and thickness. Some pieces are slivers no bigger than a coin. Others are fist-sized chunks of twisted frame. Dust clings to every surface, along with traces of paint, rubber, and oil. Before it can be melted and turned into new steel, it has to be cleaned, both physically and chemically. Many facilities use a combination of tumbling drums, magnetic polishing systems, and even high-pressure air washers to remove as much surface contamination as possible. This cleaning phase is crucial because impurities introduced at the melting stage, things like grease, silicon, or plastic, can weaken the molecular structure of the steel. The more consistent the feedstock going into the furnace, the higher the quality of the final product. In this way, the recycling process isn't just about reclaiming material, it's about restoring its integrity, making sure it can meet the rigorous standards of modern steel manufacturing. The cleaned steel scrap, often referred to now as shred, is loaded into rail cars or large industrial bins. It's typically compacted or baled into dense blocks to make transport more efficient and then shipped off to steel mills, either integrated steelworks or mini mills, depending on the region. Here, the final transformation begins. In a mini mill, which is a far more common destination for recycled steel, the melt process centers around an electric arc furnace, a piece of equipment that looks like something out of a science fiction novel. Massive, dome-shaped, and lined with refractory bricks, the furnace uses enormous graphite electrodes, sometimes over 20 feet long, to create arcs of electricity hotter than the surface of the sun. These arcs don't burn fuel. Instead, they generate heat through electrical resistance, capable of raising temperatures above 3,000 degrees Fahrenheit. When the baled scrap steel is dropped into the furnace, it begins to liquefy almost immediately. Standing near an EAF in operation, the sensory experience is overwhelming. There's a roar, like a jet engine, accompanied by bursts of brilliant white light each time the arc strikes the scrap. The air shimmers with heat, the floor vibrates, and above it all, a haze of steam and dust hangs in the air, sucked away by powerful exhaust systems. Workers stand behind heat shields or monitor the operation remotely from control rooms, watching carefully as the scrap turns into molten steel. The process isn't just about heat, it's also chemistry. Impurities in the scrap rise to the top during melting, forming a layer of slag. This slag is skimmed off, analyzed, and adjusted. Alloying agents can be added at this point, elements like manganese, chromium, or nickel, depending on the desired properties of the final steel product. It's a balancing act, and one that steelmakers have refined over generations. They're not just melting down old cars. They're creating entirely new steel grades, tailored for specific uses, rebar for construction, sheets for appliance casings, or ultra-high-strength steel for automotive frames. What's remarkable is how efficient this entire system has become. Using scrap steel in electric arc furnaces requires up to 74% less energy than producing steel from raw iron ore. It also generates significantly fewer emissions. And because modern steel doesn't degrade in quality with recycling, the metal from a 1998 station wagon can just as easily become part of a 2025 electric SUV, or the rebar holding up a 30-story apartment building. Steel is endlessly recyclable. It never wears out. It simply changes form over and over again. After the molten steel reaches the desired composition, it's tapped from the furnace and poured into molds or cast into billets, slabs, or blooms, depending on its final use. These semi-finished products are then rolled, shaped, and cooled in massive mills that can stretch for hundreds of meters. At the end of this process, the steel is often indistinguishable from that made directly from iron ore. The only difference is its origin story, and the fact that it once roamed the streets with a steering wheel and license plate. Once the molten steel is tapped from the furnace and cast into semi-finished shapes, be it billets, blooms, or slabs, it enters the next phase of its rebirth, the rolling mills. These sprawling, high-temperature production lines are among the most visually impressive spaces in the steel industry, filled with massive, glowing ingots of red-hot metal being shaped under the pressure of rollers that exert forces measured in thousands of tons. As the slabs pass through successive stages of the mill, they are squeezed, stretched, and flattened into thin sheets or long bars, depending on their intended future use. The steel at this point still carries the energy of the furnace within it, glowing orange as it's guided along mechanized tracks, each turn and motion precisely timed to ensure uniformity of thickness, strength, and grain structure. Every roll, every adjustment in temperature and tension is calculated to within fractions of a millimeter, because these seemingly raw forms will eventually serve in some of the most safety-critical and structurally demanding applications in the world. For automotive use, the steel must meet particularly exacting standards. Body panels, frames, crumple zones, and internal structural supports all demand specific grades of steel, many of which must combine lightness with exceptional strength. To achieve this, advanced steel grades are produced through controlled cooling and microalloying during the rolling phase, introducing trace amounts of elements like niobium or vanadium to alter the steel's crystalline structure. These fine-tuned metallurgical manipulations determine how the steel behaves under impact, how it resists corrosion, and how easily it can be formed into the complex curves of a modern vehicle's body. At this point, the steel, once part of a decaying sedan or a rusted-out pickup truck, is no longer simply recycled scrap. It has been transformed into an engineered material that meets or exceeds the quality of virgin steel, ready to take its place in a new product with a new life. As the newly rolled coils of automotive-grade steel cool and stabilize, they are coated in protective layers, often zinc-based, through a process known as galvanization, to guard against rust during storage, shipping, and eventual use. These coils, weighing as much as 30 tons each, are stacked and tagged with precise identifiers, allowing them to be traced back through every stage of the process, from the scrapyard to the mill floor. This level of traceability is vital in today's tightly regulated manufacturing ecosystem, where quality control is both a safety imperative and a contractual requirement. The data attached to each coil includes not only its physical dimensions and mechanical properties, but also the exact composition of its alloy, the mill it came from, the furnace heat it was produced in, and the specific parameters under which it was processed. Nothing is left to chance, because the final users, automakers, appliance manufacturers, infrastructure contractors, demand absolute reliability. Once these steel coils leave the mill, they enter the global logistics system that connects steel producers with the world's industrial users. Trains, barges, and flatbed trucks loaded with precisely wrapped coils fan out across continents, heading for fabrication plants, stamping facilities, and car factories that operate on razor-thin schedules and just-in-time delivery models. A missed shipment can delay production lines, so the movement of this material is tracked with almost military precision. In automotive plants, the steel arrives often just days or even hours before it is needed, unloaded by automated cranes and moved into position beside massive robotic presses. These machines, often standing 2 or 3 stories tall, press the steel into doors, fenders, roof panels, and internal structural supports in rapid succession, each motion calibrated to exact tolerances. The sound of the press stamping steel is deep and rhythmic, like a giant heart beating inside the factory, and the material it shapes carries within it the recycled legacy of countless vehicles that once traveled the world's roads. But it's not just body panels that are made from recycled steel. Much of a modern car's chassis, the platform that holds the suspension, engine, transmission, and passenger cabin, is constructed from high-strength steel that often originates from scrap. Even the ultra-strong, crash-resistant steels used in door reinforcements and safety cages can be derived from recycled feedstock, provided the metallurgical processing is precise. In this way, a car that once carried its last passenger to the junkyard may return, in part, as the very structure that protects someone else's life on the highway. The continuity is both practical and poetic, a cycle of material use that eliminates waste while reinforcing safety, durability, and performance. What makes this industrial cycle so remarkable is not just the transformation of matter, but the scale and speed at which it happens. Every component in the process, from the cranes that unload shredded scrap to the computer-controlled furnace arcs and automated rolling lines, is designed to maintain throughput with minimal interruption. Downtime is the enemy of efficiency, and every minute of operation is carefully optimized. Facilities that recycle vehicles into steel operate 24 hours a day, often 6 or 7 days a week, managing thousands of tons of material with fewer errors than a traditional assembly line. And yet, despite the size and power of the equipment, these operations are governed as much by software as by steel. Sensors embedded throughout the system monitor temperature, chemical composition, conveyor speeds, and output weights in real time, feeding data into central control systems that adjust operations on the fly to maintain consistency and quality. Perhaps the most surprising aspect of this process is how invisible it remains. Despite its monumental scale, the recycling of cars into steel happens largely out of sight, hidden behind the walls of industrial buildings, buried in shipping manifests, and wrapped in the form of fresh steel that looks no different from any other. The story of a recycled car doesn't leave a mark on the coil that arrives at the stamping press. And yet, embedded in that coil is a legacy of resource recovery, engineering ingenuity, and environmental responsibility that stretches across continents and decades. The result is a product that not only meets the performance standards of modern manufacturing, but does so with a significantly reduced environmental footprint. Compared to steel made from raw iron ore, recycled steel requires far less energy, produces fewer carbon emissions, and reduces the need for mining operations that scar landscapes and ecosystems. In fact, the use of electric arc furnaces powered by renewable energy is rapidly transforming recycled steel into one of the most sustainable industrial materials in the world. Some steel plants are even approaching carbon neutrality, using solar and wind energy to power their furnaces and integrating closed-loop water systems to minimize waste and pollution. These advancements are not theoretical. They are happening now, quietly and efficiently, in plants from Germany to South Korea, from the United States to China. This is the true triumph of large-scale automotive recycling, not just the cleverness of the machines or the scale of the infrastructure, but the way it silently reinvents the concept of waste. A rusted-out sedan parked in a forgotten corner of a salvage yard is not the end of anything. It is the beginning of a transformation. The same metal that once bore the brunt of time, weather, and collision becomes once again the backbone of modern civilization. Steel does not die. It endures, it bends, melts, reforms, and returns, stronger, cleaner, and ready for whatever comes next. As the global automotive industry evolves, so too does the complexity of the cars themselves. While older vehicles were largely composed of steel, glass, and rubber, modern cars are far more sophisticated composites of aluminum, high-strength steel, carbon fiber, plastics, polymers, advanced electronics, and multi-layered coatings. What once could be broken down into a few basic materials is now a carefully engineered puzzle of chemically diverse components, many of which resist separation or carry environmental risks if processed incorrectly. This shift has introduced a formidable new challenge to large-scale automotive recycling: how to maintain the efficiency and purity of steel recovery in the face of growing material complexity. A modern car is, in essence, a rolling computer. The average new vehicle contains over 1,000 chips, dozens of circuit boards, and hundreds of feet of copper wiring. Touchscreens, radar sensors, LiDAR systems, electric drive modules, and battery management units are now embedded in vehicle architecture in ways that make simple disassembly nearly impossible. While these systems enhance safety, comfort, and performance, they complicate the process of separating ferrous from non-ferrous materials downstream. Many of the components that pose the greatest hazard, such as lithium-ion batteries, rare earth magnets, or even pressurized gas canisters used in airbag systems, are invisible to the eye and integrated deeply within structural assemblies. If overlooked, they can cause fires, explosions, or chemical contamination during shredding or melting. To manage this, leading recycling facilities are beginning to integrate more advanced diagnostic systems into their dismantling stages. Some use proprietary vehicle information systems to identify make and model specific hazards before a car even reaches the yards. Using VIN decoding, technicians can pull up technical diagrams and safety bulletins, allowing them to locate and remove battery packs, airbag modules, and high voltage cables before the car reaches the shredder. In some high volume facilities, cameras mounted on robotic arms scan incoming vehicles for key identifiers, emblem locations, chassis markings, and structural features, flagging those that require special handling. It's not just about protecting workers or machines, it's about safeguarding the downstream purity of recovered steel, which must remain free from copper, aluminum, or heavy metal contamination to be viable for high-grade reuse. One of the most persistent contaminants in recycled steel is copper, introduced primarily through wiring harnesses, motors, and small mechanical components like bushings or fittings. Even tiny amounts of copper can cause significant problems when steel is melted and re-solidified. It leads to hot shortness, a phenomenon where the steel becomes brittle and prone to cracking during rolling or forming. Unlike some contaminants, copper cannot be removed once it's alloyed into the melt. That means the only defense is prevention, removing it before shredding. As a result, many shredding operations now include copper extraction stages, often using sensor-based sorting technologies such as X-ray fluorescence or laser-induced breakdown spectroscopy to detect and remove non-ferrous fragments before the steel stream reaches the furnace. These systems aren't perfect, but they represent a growing convergence of material science and machine vision that's pushing automotive recycling into a more precise and adaptable era. The same applies to aluminum, which has seen a sharp increase in automotive use over the past 2 decades. Many hoods, doors, and structural components in modern vehicles are now made from aluminum alloys, prized for their strength-to-weight ratio. However, aluminum and steel cannot be recycled together. When mixed in a melt, aluminum weakens the steel and leads to defects. So the sorting systems downstream from the shredder have grown more sophisticated in response. Eddy current separators use rapidly changing magnetic fields to induce currents in non-ferrous metals, pushing aluminum fragments away from steel, while optical sorters differentiate materials by reflectivity and elemental signature. In high-end facilities, these systems are now accurate enough to separate different aluminum grades from one another, further improving recovery value and material reuse. Despite these advances, the industry still grapples with the increasingly frequent use of composite materials. Plastics reinforced with carbon fiber, hybrid metal polymer laminates, or thermosetting resins used in structural panels and bumpers. These materials, while ideal for lightweight construction, are often unrecyclable in any traditional sense. They resist shredding, cannot be melted or reformed, and release harmful gases when incinerated. As such, they usually end up in landfill-bound residue, a byproduct known in the industry as ASR, automotive shredder residue. While many regions require ASR to be managed responsibly, it remains one of the largest waste streams in the auto recycling sector. Research is underway into thermal decomposition and chemical recycling techniques that could break down these materials into usable hydrocarbons or resins, but most are still in pilot stages and not yet scalable to the millions of tons generated annually. Amid all this complexity, the global supply chain that supports recycled steel continues to operate with astonishing resilience. Raw scrap from end-of-life vehicles is traded and shipped around the world like any other commodity. Large-scale exporters in the United States, Europe, and Japan ship scrap to steel mills in countries like Turkey, India, South Korea, and China, where demand for feedstock regularly outpaces local supply. Some of these mills specialize in certain grades of recycled steel, producing flat products for automotive use, while others create construction-grade billets for rebar and structural beams. Ships loaded with compressed scrap cubes leave ports daily, often headed for mills located near coastlines for easy offloading and reduced inland transport costs. To support this system, international standards have emerged that classify recycled steel by composition, contamination level, and form factor. These standards, maintained by organizations such as the Institute of Scrap Recycling Industries or the European Association of Metals, ensure that buyers can trust the quality of the material they receive, even if it has changed hands multiple times across borders. In many cases, shipping containers of scrap are inspected using portable spectrometers or magnetic analyzers before acceptance, creating a level of transparency and consistency that mirrors other highly regulated commodities like grains or rare earth metals. Government policy plays an increasingly pivotal role as well. In countries with aggressive emissions reduction targets, recycled steel is viewed as a key pillar in the decarbonization of industry. Regulations may include carbon reporting for virgin versus recycled content, tax incentives for using scrap feedstock, or even mandates requiring automakers to demonstrate end-of-life recyclability for all new models. In the European Union, for instance, the End-of-Life Vehicles Directive requires that 95% of a vehicle's weight must be either reusable or recyclable, pushing manufacturers to design with disassembly and material separation in mind. This kind of legislation is changing the very DNA of vehicle design, not just how cars are used, but how they are unmade. In some regions, automakers themselves are directly investing in recycling infrastructure, closing the loop on their own supply chains. Tesla, for example, has explored in-house battery recycling, While companies like BMW and Volkswagen have partnered with material recovery firms to ensure access to clean, high-quality, recycled metals. For steel, this means building partnerships with mills that specialize in low contamination, automotive-grade scrap, or even incorporating scrap return systems, where offcuts and press waste from vehicle production are sent back to the steel mill for reprocessing. These circular economies don't just reduce cost, they create supply stability in an increasingly volatile raw materials market. What becomes clear as you trace the journey from junkyard to steel mill to factory floor is that this system is not a linear chain, but a loop, a continuously rotating wheel of consumption, reclamation, and reinvention. And within that loop, steel holds a privileged place. Unlike most materials, it can be recycled indefinitely without degradation, offering infinite life cycles with no loss in performance. Every time it is melted, reformed, and reused, it emerges just as strong, just as resilient as the day it was first forged. It is the backbone of industry, but also one of its most elegant solutions to waste. Behind the towering machines, the roaring furnaces, and the endless streams of metal, there is another force that keeps the car recycling process alive: human labor. For all the automation, all the robotic arms, shredders, and sensors, none of this works without the people who oversee, calibrate, and respond to the constant complexity of industrial recycling. From the dismantlers working in salvage yards to the control room engineers monitoring furnace conditions in real time. Every stage of this operation relies on skill, precision, and a deep, often hard-earned understanding of the materials they handle. The process may look mechanical from a distance, but up close, it's anything but impersonal. At the beginning of the line, in the yards and dismantling stations, work is loud, physical, and dirty. Vehicles arrive caked in grime, filled with the leftovers of long lives, coffee cups under seats, shattered glass in door panels, soaked carpets, animal nests under hoods. Before the metal can be touched, the contents must be made safe. This means draining fluids, removing hazardous electronics, and locating anything that could ignite, explode, or contaminate the system further down the line. The work here is not glamorous, but it is essential, and the people who do it are often mechanics turned specialists, using a combination of brute strength and technical finesse. Removing a battery pack from a hybrid SUV isn't just a matter of unplugging wires. It requires voltage testing, insulated tools, and training in high voltage protocols, all carried out in cramped spaces with sharp edges and years of accumulated rust. In cold months, metal tools stick to gloved hands. In the summer, the heat rising from concrete and steel can make even simple tasks exhausting. And yet, across yards from Detroit to Dusseldorf, from Sao Paulo to Seoul, this work continues every day. The workers know exactly where to pry open panels, how to remove fasteners without destroying a valuable part, and which parts can be sold before the shell goes into the shredder. Some facilities incentivize efficiency by linking wages to recovery rates. The more value salvaged, the higher the take-home pay. This creates a rhythm, a learned intuition, passed between workers, refined over years. It's a choreography of motion. Drain, remove, lift, strip, all before the steel moves on. As the vehicle shell is reduced to scrap and fed into the shredder, another team takes over. Operators watch from a reinforced control room, often through bulletproof glass, as the crane drops each car into the shredding chamber. They monitor the vibration of the machine, the temperature of bearings, the motor load, and the speed of the conveyor belts, making adjustments in real time to prevent overloads, fires, or mechanical wear. If anything unexpected happens, like a stray propane tank left in a trunk, the results can be violent. Shredder explosions are rare but dangerous, and entire teams are trained to detect the early warning signs: sudden pressure spikes, unusual acoustic signatures, or irregular feedstock behavior. There is a quiet tension in these rooms, like air traffic control for machines that can crush an engine block in seconds. Further down the line, the material sorting systems are a fusion of mechanical design and human intervention. Although much of the separation is handled by magnets, sensors, and compressed air jets, humans are still required to supervise, verify, and intervene when things go wrong. Belt operators watch for jams, pick out missed items, and monitor the calibration of the sorting machinery. Engineers and maintenance teams walk the line daily, checking for worn bearings, frayed wires, and the small signs of wear that could lead to catastrophic downtime. Many of these systems run nearly non-stop, 24 hours a day, 6 or 7 days a week, and maintenance becomes a kind of religion, an obsessive focus on the little things that keep thousands of tons of material moving without pause. Safety, too, is omnipresent. Industrial recycling carries all the risks of heavy industry: high voltage, sharp metal, rotating equipment, high temperatures, toxic fumes, and crushing force. Workers are trained not just once, but constantly on lockout procedures, emergency evacuations, chemical handling, and first aid. Signs in multiple languages dot every wall. Beware arc flash, lock before entry, hot surface, crushing hazard. PPE is mandatory, but more than that, situational awareness is drilled into every shift. A moment of distraction near the shredder or furnace can be fatal, and the workers know it. They communicate through hand signals, radio check-ins, and the practiced routines of experienced teams that trust one another because their safety depends on it. In the steel mills, the human role becomes more technical. Metallurgists oversee the quality of the molten steel, using spectrographic analysis to ensure the melt is within tolerance. Furnace operators guide the power input, adjusting current, voltage, and electrode distance to manage the intense energy environment inside the electric arc furnace. They monitor the chemistry of the slag, tweak the oxygen lances, and track the reaction of alloying elements in real time. There's a rhythm to this work too, but it's governed by data as much as by feel. Operators might work from behind thick glass or from control rooms filled with monitors, keyboards, and thermal imaging displays. They aren't handling molten steel directly, but they are responsible for its behavior, and they carry the burden of quality and consistency across every batch. And in the rolling mills, where red-hot slabs of steel are squeezed into precise forms, another layer of labor oversees the interplay between heat, force, and geometry. Rolling operators time the entry of each slab into the rollers, adjust pressures, and monitor the cooling rate to control the microstructure of the steel. Misalignment or temperature errors can lead to warped products, cracks, or internal stresses that may not reveal themselves until weeks later during use. The machinery here is massive, but its operation is precise, and the people who manage it have learned through years of experience how to listen to the line, not just visually, but through sound, vibration, and the subtle cues that machines. The process begins not with cleanliness or order, but with sheer volume and disorder. Truckloads of used bottles arrive at the facility from municipal collection systems, curbside recycling programs, and commercial waste streams. Each load a riot of colors, shapes, and materials, often coated in food residue, sticky with sugary liquids, and tangled with other forms of plastic waste, like bags, wrappers, or film. These trucks back into enormous unloading bays and dump their contents into vast concrete pits or onto initial conveyor lines that snake their way toward the first stage of the system. At this point, the factory doesn't attempt to finesse anything. It simply moves mass, pushing tons of material onto belts that carry them upward into what's known as the pre-sorting zone. Here, air knives, industrial strength jets of air, blast lightweight contaminants like shredded plastic film, paper labels, and grocery bags out of the mix, while rotating drums sift out dirt, broken glass, and small fragments that would interfere with downstream processes. The goal in this early stage isn't to achieve purity, but to remove the most obvious and problematic debris, to protect the far more delicate machinery that comes later in the line. Once through this initial triage, the bottles pass under a series of powerful magnets and eddy current separators designed to extract metal objects, caps with aluminum liners, bits of wire, or even the occasional misplaced food can that could damage shredders or grinders further down the line. Everything in this stage is loud, aggressive, and unapologetically utilitarian. It's about brute force and filtering, with machines built to operate continuously for weeks without shutdown, enduring abrasion, impact, and dust as they process tens of thousands of bottles per hour. Even now, the system remains non-specific. It doesn't care yet whether a bottle once held juice or shampoo, whether it's colored green or blue or clear. That level of discernment comes later. For now, the factory simply wants to reduce the chaos into a stream that can be sorted more intelligently. As the material continues along the conveyor, the next major transformation occurs in the form of optical sorting, an astonishingly high-tech stage where each individual bottle is scanned by near-infrared sensors and high-speed cameras capable of identifying the molecular composition of the plastic within milliseconds. These machines are not guessing. They are performing real-time spectroscopy, recognizing the unique signatures of PET, polyethylene terephthalate, HDPE, high-density polyethylene, PVC, and other polymers, and then triggering precisely timed puffs of air that blast each item into its appropriate chute. Clear PET bottles go one way, green another, HDPE milk jugs yet another, while problematic materials like PVC, which can contaminate entire batches if allowed through, are shunted off to waste bins for specialized disposal. It's a mesmerizing process to watch. An endless stream of spinning, bouncing plastic forms flowing beneath a sensor array that dances with flashes of light and jets of air, sorting thousands of items per minute with astonishing accuracy. And while the human eye would be overwhelmed by the sheer speed and variety of the objects passing by, the machines remain indifferent, tireless, and utterly precise, driven by algorithms that learn and adjust with each pass. This sorted stream of PET bottles, now largely free of foreign plastics and metals, is ready for one of the most transformative stages of the entire process: shredding. The bottles, still intact and recognizable in shape, are fed into enormous rotary grinders, machines that can span the length of a car and house dozens of hardened steel blades rotating at high velocity. These grinders don't so much cut the bottles as annihilate them, turning rigid plastic into small, irregularly shaped flakes that fall like confetti onto vibrating screens. This is the first moment where the bottles lose their identity, ceasing to be discrete objects and becoming raw material, jagged, frosted flakes that will undergo further refinement before they can be deemed useful. But despite their fragmented state, these flakes are still filthy, still covered in sticky residues from soda syrups, juice sugars, and whatever grime the bottles encountered along their journey from consumer to truck to facility. So the next phase, washing, is as critical as it is elaborate. This isn't just a rinse under a tap. The plastic flakes enter a washing system that's closer in complexity to a small water treatment plant than anything found in an ordinary kitchen. The process often begins with a hot water pre-wash, where the flakes are agitated in large heated tanks to soften and remove surface grime. Next, they pass through a series of friction washers, long cylindrical drums filled with rapidly spinning paddles that slam the flakes against each other and the drum walls, scrubbing them clean through mechanical abrasion. From here, they enter float sink tanks filled with water calibrated to a specific density. PET flakes sink, while caps, labels, and HDPE contaminants float to the surface and are skimmed away. This clever use of relative density is one of the most effective and low-tech solutions in the entire factory, allowing for a clean and reliable separation without a single sensor or line of code. After several rounds of washing, rinsing, and sometimes even chemical baths to remove persistent adhesives or inks, the PET flakes are dried in high-speed centrifugal dryers. Imagine a washing machine spin cycle scaled up to industrial proportions, leaving them clean, dry, and ready for transformation. At this point, we're barely halfway through the process, but already the journey from bottle to raw material has revealed just how much infrastructure, energy, and precision goes into something most of us imagine as a simple matter of putting it in the blue bin. The plastic is no longer trash. It's now a valuable commodity, washed, sorted, and ground into flakes that glisten slightly under the overhead lights. Smelling faintly of warm plastic and citrus cleaner, ready to be melted, filtered, and formed into something entirely new. What happens next will push this material to its physical limits, remelting and reshaping it at temperatures approaching 270 degrees Celsius, filtering it through microscopic screens, and turning it into perfect, uniform pellets that will form the building blocks of new products. And it all unfolds with an elegance and intensity that reflects the very best of modern industrial design. The cleaned and dried PET flakes, now stripped of their former identities as soda bottles, water jugs, and juice containers, move into one of the most critical and tightly controlled phases of the recycling line: extrusion and pelletizing. This is where solid flakes are transformed back into a raw material suitable for manufacturing. But unlike earlier stages that relied on brute force and separation, this phase is about precision engineering at the molecular level. Every parameter, from temperature to pressure to filtration, is fine-tuned to ensure consistency, because the goal here isn't just to recycle plastic, it's to restore it to a form so pure and standardized that it can compete with virgin resin made directly from petroleum. The flakes are fed into massive stainless steel hoppers that funnel downward into twin-screw extruders, towering machines where heat and compression converge in a kind of controlled plastic alchemy. Inside, intermeshing screws rotate within heated barrels, gradually increasing pressure and temperature until the flakes begin to soften, melt, and finally merge into a viscous, honey-like stream of molten plastic. This material, thick and gleaming, is pushed forward along the barrel, where it passes through fine mesh filters, ultra-strong screens that catch any remaining contaminants, bits of paper, or unmelted residue that survived earlier stages. These filters are automatically cleaned or changed by robotic systems to maintain flow without downtime, because in factories like these, time is measured in throughput, and a single minute offline can mean a ton of lost material. Once filtered, the molten plastic is pushed through a die plate at the end of the extruder, emerging in long, spaghetti-like strands that are immediately cooled, typically by passing through a chilled water bath. These strands are then cut into uniform plastic pellets by high-speed rotary knives, a moment that feels both violent and elegant as hardened blades slice through the warm polymer at just the right angle, and pressure to produce identical, perfectly shaped granules. These pellets, known in the industry as recycled PET resin, rPET, are what it's all been leading up to: the reusable, moldable currency of plastic manufacturing. They tumble out in a rush, warm to the touch and slightly translucent, each one a fingerprint-less blank slate ready to become packaging, textiles, or even new bottles all over again. But in facilities dealing with food-grade recycling, the process doesn't stop there. Regulations are exacting when plastic is meant to come into contact with food or beverages again. So a specialized additional phase kicks in: super cleaning, a complex series of thermal and vacuum treatments that strip the plastic of any lingering contaminants at the chemical level. The pellets are heated under vacuum conditions to force out absorbed gases, volatile organic compounds, and anything else that might have bonded with the plastic during its first life. In some systems, they're also subjected to solid-state polymerization, SSP, a process where heat is applied below the melting point to rebuild molecular chains broken during the first production and recycling phases, essentially restoring the mechanical properties of virgin plastic. The result is a recycled resin that's strong, clean, and fully certified for use in food and beverage packaging, something increasingly important as industries seek to close the loop on plastic waste. Meanwhile, the factory operates on a rhythm, a tempo dictated by conveyor belts, shift schedules, and the constant roar of machinery. There's a tactile hum to the place, the vibrations of motors through the concrete floor, the occasional hiss of hydraulic arms adjusting alignment, the smell of warm plastic mingled with faint industrial lubricants. Operators move through this space like engineers aboard a spacecraft, monitoring temperatures on digital panels, checking quality samples from pellet bins, recalibrating machines with a keystroke or a wrench. Some areas are entirely automated, sealed behind glass, where robotic arms handle material with a speed and delicacy no human could match. Others require manual checks, technicians pulling pellets every half hour for lab testing, inspecting them under microscopes to measure clarity, size distribution, and contamination levels, down to parts per million. It's a blend of the analog and the automated, and the balance is crucial. One bad batch, one jammed extruder, one missed contaminant could mean hours of downtime and thousands of kilograms of compromised product. And yet, the most fascinating part isn't the pelletizing itself, it's the scale. A single industrial recycling line can process over 50,000 kilograms of plastic per day. That's the equivalent weight of more than 2 million empty water bottles, shredded, washed, melted, and reformed into tiny granules in a single 24-hour cycle. Multiply that by the number of lines operating simultaneously in one facility, and then again by the number of such plants operating around the world, and you begin to grasp the staggering logistics involved in trying to intercept just a fraction of the world's plastic waste before it ends up in landfills or the ocean. But what happens to all these pristine rPET pellets once they're finished? They're not stored long. Most are loaded directly into bulk transport systems, either funneled into massive silo containers or poured into specialized trucks with sealed, dust-free interiors that carry them to manufacturers. In many cases, the recycling facility is co-located near or even integrated with plants that produce bottles or plastic components, forming a closed-loop supply chain that eliminates unnecessary transport and reduces emissions. In other setups, the pellets are shipped globally, especially to textile factories that convert rPET into fibers for clothing, carpet, insulation, and even automotive fabrics. What began as a discarded water bottle might soon become the lining of a winter jacket or the stuffing inside a car seat. Its physical structure changed, its purpose entirely reinvented, but its material essence preserved. Still, not everything in the stream becomes pristine pellets. Even in the best designed facilities, residual waste builds up. Labels that resisted removal, caps made from incompatible polymers, multi-layer packaging with embedded metals or barriers, and the occasional, non-recyclable contaminant that made it through every stage undetected. These leftovers are collected and separated into their own streams. Some are incinerated for energy recovery in waste-to-power systems. Others are landfilled, and a growing portion is being sent to advanced recycling plants that use chemical processes like pyrolysis or gasification to break plastics down into their basic hydrocarbons. These methods are still controversial and developing, but they represent the cutting edge of what could become a more circular plastic economy, where even the least recyclable materials can be transformed into useful feedstocks rather than waste. And then there are the outliers, the moments when something unexpected emerges from the line. A message written on a label in permanent marker. A bottle still half full of ancient soda, syrupy and fossilized. A branded sports drink container from a country across the world, somehow swept up in the tides of global trade and municipal waste management, now ground and melted in a factory on the other side of the planet. These anomalies remind workers, even in an environment dominated by automation and efficiency, that every piece of plastic was once held in a hand, used in a moment, and discarded with the silent hope that someone, somewhere, would make it useful again. To truly appreciate the scope and sophistication of a modern plastic bottle recycling facility, you have to look past the movement of material and into the engineering bones of the system, the machinery that orchestrates each phase with precision, the systems that regulate flow and temperature to within fractions of a degree, and the software that keeps it all running in sync, often without a single second of unplanned downtime. These factories are, in every sense of the word, machines themselves, giant living systems built to consume chaos and output order. Take the infrared sorting units, for example. While they may appear, at a glance, to be nothing more than long metallic chutes with blinking lights and conveyor belts, their internal systems are more akin to laboratory spectrometers than industrial hardware. As bottles pass beneath their sensors, high-intensity halogen lamps flood the stream with near-infrared light, which penetrates each object and bounces back with a molecular signature unique to the plastic type. This data is processed in real time, measured, matched, and acted upon in milliseconds, triggering microscopic blasts of compressed air that redirect each item with shocking accuracy. These air jets are positioned just centimeters apart and fire with exact timing, often making dozens of adjustments per second. The calibration is so fine that even labels or caps can be identified and accounted for, ensuring that only the correct plastic types move forward to shredding. The complexity of this system is further increased by the color sorting modules, which run in parallel. Color affects the value and reusability of plastic, and the market for clear PET is vastly stronger than for green or blue. So the optical sorters don't just see molecular structure, they also see hue, tone, and tint, all while handling material at speeds exceeding 3 meters per second. Further down the line, the grinding units, commonly referred to as granulators, represent a completely different class of machine. Blunt, powerful, and built for raw force. The interior chamber of a granulator houses a rotor embedded with multiple sets of hardened steel blades, rotating at high speed within a tight cutting gap against stationary blades affixed to the chamber wall. The bottles are fed in whole, and as the rotor spins, the plastic is sliced and crushed into flakes. But it's not a simple cut and done process. Every few seconds, the machine experiences varying loads depending on bottle density, cap rigidity, or even residual liquids inside. To manage this variability, granulators are equipped with torque monitors, automatic load sensors, and hydraulic systems that adjust blade distance on the fly, ensuring the flakes are cut to the correct size and minimizing unnecessary wear. Even the steel used for the blades is carefully chosen, often a specific tool-grade alloy hardened to withstand continuous impact across weeks of uninterrupted operation. And when those blades do dull, which they inevitably will, robotic maintenance arms or skilled technicians perform hot swaps during scheduled micro pauses, typically under 15 minutes, to avoid halting the rest of the line. Once the plastic reaches the washing section, the engineering shifts again from mechanical force to fluid dynamics. Friction washers, perhaps the most underestimated machines in the plant, rely not just on high-speed agitation, but also on precisely engineered turbulence. Their interior surfaces are ribbed and often sloped to enhance directional flow, while the spinning paddles create vortex-like conditions that scrub the flakes against one another, dislodging oils, adhesives, and microscopic grime. But these systems face an uphill battle. Labels and glues, especially on shrink-wrapped bottles, are notoriously difficult to remove. Some factories deploy pre-treatment systems using steam or mild caustic solutions to soften adhesives before friction washing, while others rely on enzymatic soaks that break down organic contaminants without damaging the plastic. This introduces its own set of challenges. Temperature control becomes paramount, as enzymes are highly sensitive to heat, and if the wash water strays above their threshold, the cleaning power is lost. To counter this, inline heaters and chillers maintain the water at precise set points, often within a 1 degree Celsius window, and flow regulators ensure consistent agitation regardless of load volume. Behind all of this is a nerve center, often tucked away in a control room that overlooks the factory floor through thick glass and glows with the light of a dozen screens. Here, plant operators monitor every variable: flow rates, contaminant levels, energy consumption, downtime intervals, and machine health metrics. Predictive maintenance algorithms flag potential failures before they occur, using vibration data and power usage signatures to anticipate motor wear or blade fatigue. Machine learning models, trained on historical data, adjust sorter sensitivity based on the material stream in real time, compensating for seasonal shifts in recycling input. More water bottles in summer, more detergent containers in winter, more unusual contaminants after festivals or holidays. This is not a simple assembly line. It is a data-driven ecosystem where automation and analytics intertwine to keep the process lean, efficient, and remarkably responsive. Yet for all the technology, one of the most remarkable aspects of the system is how it handles hygiene and contamination control. Recycling is inherently dirty business. Bottles arrive sticky, smelly, and often carrying biological waste or mold. To ensure that these contaminants don't interfere with pellet purity, especially for food-grade applications, factories implement strict zone controls. The plant is typically divided into sections: raw waste, intermediate product, and clean output. Personnel moving between zones must follow sanitation protocols, not unlike those in pharmaceutical facilities. Some areas require boot dips, hand sanitizers, or full PPE transitions. In food-grade lines, air is filtered through HEPA systems to remove dust and microbes, and machinery is sanitized on scheduled rotations with pressurized steam or chemical disinfectants. These steps aren't just for show. If a batch of food-grade rPET is found to be contaminated, it can't be downgraded. It must be destroyed, which means hours of work, energy, and material lost in an instant. The cost of a single sanitation failure can stretch into the tens of thousands of dollars. Then there are the safety considerations. Between high-speed blades, heated extruders, and pressurized air systems, the factory is filled with risk zones. Every moving part is shielded with interlocked guards, which shut down machines if lifted. Emergency stops are distributed across every few meters of conveyor, and sensors constantly scan for jams, spills, or foreign objects that might pose a danger. In some systems, AI-powered cameras monitor for smoke or overheating and can trigger halon gas suppression in case of electrical fires. Worker safety is non-negotiable, not just because regulations demand it, but because any injury halts production and creates cascading problems across the line. All of these systems, mechanical, digital, human, cooperate in a tight choreography, each component dependent on the one before and after. A failure in the sorting stage affects the quality of grinding. A clog in the washing line delays drying. A hiccup in pelletizing can ruin an entire shift's output. And yet, despite this complexity, some of the most advanced factories operate with less than 10 full-time operators on the floor per shift, thanks to layers of automation and smart monitoring. These aren't chaotic places. They are symphonies of movement and control, calibrated down to the second and refined over years of continuous improvement. And the numbers tell the story best. In a single 24-hour period, a mid-sized facility might process 600,000 bottles, producing enough clean rPET pellets to manufacture over 400,000 new containers. Across a year, that same facility might divert 150 million bottles from landfill or ocean-bound waste, turning them instead into feedstock for new products. It's not a perfect system. Contamination still occurs. Not all plastics are recyclable, and market demand fluctuates. But it represents one of the most ambitious efforts humanity has made to bend the life cycle of plastic back towards sustainability, using sheer engineering prowess and logistical finesse. Once the pellets are dried, screened, and approved, the final product, rPET, ready for reinvention, moves from the factory floor into a world of relentless logistics. Here, the engineering shifts from mechanical systems to supply chain choreography. The recycled pellets, still faintly warm from their creation, are stored in vast silo tanks, often towering 2 or 3 stories high, each capable of holding tens of thousands of kilograms of plastic. These silos are not just containers, they are pressure regulated, sealed from ambient humidity, and monitored 24/7 for temperature and moisture content. Even the tiniest change in air conditions could compromise pellet quality, especially if the plastic is destined for food-grade applications. Some facilities pipe warm, dry nitrogen into these silos to displace oxygen and prevent oxidation. Others use vacuum systems to move pellets directly from the extrusion lines into sealed containers, never exposing them to open air. It's a level of care that would seem obsessive if the stakes weren't so high, because one contaminated truckload, once it leaves the factory, is often unsalvageable. Shipping is both art and science. In many high-throughput facilities, pellets are loaded into pneumatic transport trucks, where air pressure drives the material up and through stainless steel, piping into the storage compartments of the vehicle. The sound of pellets rushing through steel tubing is distinct, like a quiet avalanche, constant and granular, echoing slightly as it winds through the system. Each load is weighed, barcoded, and logged digitally into the plant's ERP, Enterprise Resource Planning, system, where every kilogram is traceable to the batch of bottles it came from. These records are critical. Manufacturers who buy rPET need to verify not just purity and quality, but chain of custody, proof that the plastic was collected, sorted, and processed according to specific environmental and safety standards. This is particularly important in regions governed by circular economy regulations or tax incentives for using certified post-consumer recycled material. Some of the recycled plastic stays local, especially in facilities located near large-scale bottle manufacturers or packaging plants. In these setups, the rPET pellets might travel less than a kilometer before being fed into new injection molders or blow molding machines, where they're reformed into preforms, the test tube-like shapes that are later inflated into bottles. It's a closed-loop system in the truest sense, where yesterday's drink container becomes tomorrow's within a matter of days, often without ever leaving the industrial park. In other cases, the pellets are shipped overseas, packed into bulk containers, and sent to textile factories in Southeast Asia, Eastern Europe, or the southern United States. There, the plastic is reheated, extruded again, this time into long continuous fibers thinner than human hair, and spun into threads for clothing, carpeting, or insulation. 1 ton of rPET can be spun into over 75,000 meters of polyester fiber, enough to make 2,500 fleece jackets or line dozens of cars with sound-absorbing material. The diversity of rPET applications is one of the great triumphs of the recycling ecosystem. Beyond bottles and textiles, recycled plastic finds its way into automotive interiors, building materials, electronic casings, and even 3D printing filament. It's durable, versatile, and, when produced to high standards, virtually indistinguishable from virgin resin. Yet the pathways aren't always simple. Manufacturers using recycled feedstock face unique challenges: color variation from inconsistent batches, trace contaminants that affect molding behavior, and regulatory hurdles that differ from country to country. That's why the factory's job doesn't end at pellet production. It continues through data sharing, quality assurance, and ongoing collaboration with buyers to fine-tune the material to exacting specifications. Some buyers require pellets with specific intrinsic viscosity (CV) levels, which relate to how the plastic flows when melted. Others want detailed reports on heavy metal content, additive residue, or UV stabilization history, and the recycling plant delivers, all of it logged, tested, and verified with laboratory precision. While the plastic moves outward, material that didn't make the cut takes its own route. Every factory produces a secondary stream: scrap, residue, and mixed waste that couldn't be sorted or cleaned adequately. In forward-thinking facilities, even this material is captured for downcycling. Contaminated PET might be repurposed into strapping tape, injection molded containers, or construction-grade plastic lumber uses where perfect clarity or purity aren't necessary. Alternatively, these lower-grade plastics are sent to chemical recycling facilities where they're broken down to their molecular building blocks using high heat and catalysts. These processes, pyrolysis, depolymerization, gasification, are still emerging technologies, but they offer promise in dealing with the stubborn, non-recyclable portion of the plastic waste stream that mechanical recycling can't touch. The goal is full circularity. No waste, no landfill, no incineration unless absolutely necessary. Still, it's not just the plastic that flows through this system. It's also data. Each batch of recycled material generates a digital footprint: timestamps, temperature logs, quality metrics, energy consumption records, machine performance data. This information is invaluable, not just for compliance or traceability, but for optimization. With AI-assisted platforms, plant managers can analyze trends across shifts, detect inefficiencies in specific machines, predict maintenance needs, or experiment with new process parameters without ever touching a physical switch. It's not uncommon for a plant to fine-tune water temperature in friction washers by less than half a degree based on energy cost trends and performance feedback, or to adjust the airflow on a sorting machine by a single percent to accommodate a subtle seasonal change in bottle coloration. These tweaks are invisible to the human eye, but represent the relentless pursuit of efficiency that defines modern industrial recycling. One of the most fascinating aspects of these factories is the way they handle volume fluctuations. Recycling plants must be adaptable. Material input is never perfectly steady. A public event, like a marathon or festival, can cause local recycling volume to spike. A sudden supply chain disruption, like a shipping backlog or labor strike, might cause bottle deliveries to pause entirely. To deal with this, many facilities are designed with buffer zones, storage bunkers, or overflow conveyors that can hold hours or even days' worth of material. In times of high input, these buffers absorb excess volume and release it gradually to keep the line running smoothly. In times of low input, the plant draws from this reserve to maintain constant output and avoid shutting down expensive systems. Some factories even coordinate with material brokers or waste aggregators in real time, adjusting pickup schedules and market prices to stabilize their inbound supply. All of this, the machines, the systems, the logistics, the oversight, culminates in a daily miracle. Waste transformed into resource, disorder shaped into uniformity, one-time use products given new purpose. It's not glamorous, it's not clean, and it's rarely appreciated. But behind every recycled bottle, every polyester shirt made from old soda containers, is a vast network of machines, people, and decisions operating in synchrony, powered by an almost obsessive attention to detail and a fierce commitment to circularity. Yet despite everything, the system is still playing catch-up. Only a fraction of the plastic we use ever makes it to facilities like this. Contamination, infrastructure gaps, and market economics continue to limit how much is recycled, how efficiently, and where. But every pellet produced, every ton diverted from landfill, every bottle reborn. These are not just technical victories, they are statements of possibility. They show what can happen when human engineering and environmental urgency converge in a process that, at its best, borders on the sublime. Once the pellets leave the facility, sealed in silos, bulk loaded into trucks, or packed into ocean freight containers, they scatter outward into the arteries of global manufacturing. And here, in this sprawling second act, the true reach of rPET reveals itself. What began as an empty water bottle discarded into a curbside bin in Los Angeles might, within weeks, become a synthetic fiber in a jacket sewn in Bangladesh, or the transparent body of a fresh shampoo bottle molded in a Polish bottling plant. The transformation is not only physical, it's economic, geopolitical, and deeply woven into how modern supply chains operate. In fact, the demand for high-quality, recycled PET has grown so rapidly that manufacturers now compete for it like a commodity, trading it across borders, pricing it by purity and certification, tracking it like gold with blockchain-style traceability systems. In the textile industry, rPET is a game changer. Factories that once relied solely on virgin polyester now blend or even fully switch to recycled plastic fibers to meet corporate sustainability goals and satisfy consumer demand for ethical materials. The process begins by melting rPET pellets again and extruding them through microscopic nozzles called spinnerets, creating long continuous filaments of polyester yarn. These fibers can be dyed, woven, knitted, or textured, depending on the application. They're found in everything from athletic wear and fleece jackets to home insulation, furniture filling, and even non-woven medical fabrics. The texture and performance of rPET fiber are nearly indistinguishable from virgin polyester, but its story is entirely different. It carries the memory of having once been something else, a disposable object transformed through precision, heat, and willpower. In packaging, the stakes are even higher. Here, recycled PET is being used more and more to create new bottles from old ones, a practice known in the industry as bottle-to-bottle recycling. But this is no small feat. To create a beverage container that is not only transparent and sturdy, but also food safe, the input plastic must meet the most stringent quality controls of any recycled material stream. Trace contamination, even at the parts per billion level, can compromise safety or affect the taste and smell of the beverage inside. To achieve the necessary standards, factories must certify their rPET under programs like the FSA, European Food Safety Authority, or the FDA's No Objection Letter system in the US. These certifications require not only process validation, but ongoing audits, documented controls, and full traceability from collection to pellet. It's an exacting process, but the reward is enormous. When done correctly, bottle-to-bottle recycling creates a closed loop where plastic circulates indefinitely through the economy, never touching landfill, never entering the ocean, never degrading in value. In the most advanced setups, the loop is literal. Some beverage companies have started building their own dedicated recycling plants, vertically integrated systems where the same corporation that bottles the drink also recycles the empty container, reprocesses it, and molds it into a new bottle. These operations often run alongside their bottling plants, with waste coming in on one side and fresh preforms leaving on the other. It's a clean, contained circle. But this model, as efficient as it is, remains relatively rare. The vast majority of rPET still relies on fragmented systems, independent recyclers, third-party transporters, global manufacturers, all exchanging material across borders, currencies, and regulations. And it's within this complexity that the system shows both its brilliance and its fragility. Because recycling, for all its engineering elegance, is still subject to market forces. When oil prices drop, virgin PET becomes cheaper, sometimes undercutting the cost of recycled plastic despite its higher environmental impact. When collection systems falter due to labor shortages, political unrest, or underfunded infrastructure, input volumes to recycling plants dip, threatening their viability. And when consumer behavior shifts, driven by trends, misinformation, or panic over microplastics, the entire ecosystem can lurch. In short, recycling is not just a technical process. It is an economic balancing act, constantly adjusting to policy, demand, and perception. Still, progress continues. Across the globe, new laws are tightening the requirements for recycled content in packaging. In the European Union, by 2030, all plastic bottles must contain at least 30% recycled content. Similar mandates are spreading to the US, Japan, South Korea, and parts of Latin America. These laws have spurred investment into both capacity and innovation. More lines, better sorters, new chemical recycling plants, and smarter collection systems. And perhaps most importantly, they're forcing manufacturers to think not in terms of isolated product life cycles, but in material loops, where every gram of plastic must be accounted for from creation to disposal and back again. At the core of this shift is a radical idea that waste is not the end of a story, but its beginning. That the bottle crushed underfoot on a hot sidewalk, the one tossed absent-mindedly into a bin or worse, not at all, that bottle still has value. That if engineered properly, managed correctly, and collected responsibly, plastic can become what it was never designed to be: circular. It's a humbling notion because it requires more than machines. It demands intention. Someone has to design that first bottle for recyclability, choosing materials that separate easily, printing labels that wash off cleanly, avoiding dyes or additives that cause trouble down the line. Someone has to fund and build the infrastructure to collect it. Someone has to operate the plant, manage the waste, fix the blades, sample the resin, and make sure that every input finds its proper path. And then, someone, perhaps far away across an ocean or on another continent, has to mold it into something worth using again. This is the hidden collaboration that defines the plastic recycling loop, not just between engineers and operators, but between consumers, regulators, investors, designers, and waste haulers. Each plays a part, knowingly or not, in keeping the material alive. And it's a delicate choreography. Break any link in the chain and the loop fails, but keep it intact and you get something remarkable. A synthetic material that, despite being man-made and non-biodegradable, can be reused over and over without loss of performance or integrity. The numbers, when scaled, are staggering. A single bottle-to-bottle rPET plant running at full capacity might recycle up to 2 billion bottles per year. Globally, the rPET market is expected to surpass $15 billion USD within the next few years, driven by packaging, apparel, and legislative mandates. And for every ton of plastic that is recycled, instead of landfilled or incinerated, the world avoids roughly 1.5 tons of CO2 emissions, a quiet, steady contribution to the fight against climate change. Multiply that by the millions of tons of plastic processed annually, and the environmental benefit becomes impossible to ignore. But perhaps the most striking thing about this entire system is how invisible it is to most people. The machines, the heat, the labor, the science, so much of it happens far from public view. Bottles disappear into bins, and new ones appear on shelves with no obvious connection between the two. And yet, beneath that surface lies a process more intricate than most manufacturing operations, more globally entangled than most supply chains, and more critical to sustainability than most realize. It's a story of hidden continuity, a narrative of material resurrection that runs quietly beneath the surface of everyday life.